Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are drifting toward one of the largest questions a human mind can hold without needing a very strong cup of tea. What is beyond the observable universe? Not just beyond Earth or beyond the Milky Way or beyond the galaxies we can photograph with our most powerful telescopes, but beyond everything whose light has had time to reach us since the beginning of the universe, beyond the edge of what we can see, beyond the cosmic horizon. It is a question that sounds at first like something from science fiction, the sort of thing whispered by someone staring out of a spaceship window while dramatic music plays in the background. But it is also a real scientific question, and a surprisingly gentle one, because it begins with a very simple fact. We do not see the universe as it is everywhere. We see the part of it that has been able to send us light. Everything else may be out there, doing whatever galaxies and space and matter do when we are not around to inspect them. But for now it remains hidden from us, not by a wall or a border or a locked door, but by time itself. And that is rather humbling, is it not? We live inside a kind of glowing bubble of knowledge, surrounded on all sides by a much larger darkness that may not be empty at all. Before we begin floating toward that horizon, I would love to know where you are listening from tonight. Are you in a city with lights outside the window or somewhere quiet where the night sky can still show itself properly? And when you look upward, do you ever get the feeling that the sky is not just above you, but around you in every direction, as though Earth itself were a tiny cabin lantern in an enormous dark field? If you find this kind of slow, scientific wandering soothing, or if it gives your thoughts somewhere peaceful to settle at the end of the day, I would be very grateful if you liked the video and perhaps subscribed. It helps this little corner of calm reach other curious minds who may also be lying awake, wondering what is outside the part of the universe we can see, and whether the answer is more galaxies, other kinds of worlds, or something stranger still. Now, I do hope this question does not keep you too alert. It is a large one after all. But we will take it slowly, step by step, with no rush at all, because the universe has been expanding for billions of years and can probably wait a few more minutes while we get comfortable. So settle in, let the day loosen its grip, and let us begin with the view from home. When people hear the phrase observable universe, it is easy to imagine a kind of boundary out there in space, like the edge of a map where old sailors might have written "here be dragons," or at least "here be very confusing astrophysics." But the observable universe is not a physical edge. It is not a shell you could fly up to and tap with your knuckles. It is not a glass dome around everything we know, though that image would be very convenient for textbook illustrators, and slightly worrying for birds. The observable universe is simply the region of the universe from which light has had enough time to reach us. Since light travels at a finite speed, looking far away is also looking back in time. The moon appears to us as it was a little over a second ago. The sun appears as it was about 8 minutes ago. Nearby stars appear as they were years ago. Distant galaxies appear as they were millions or billions of years ago. So when astronomers turn their telescopes toward the deepest parts of space, they are not just collecting light from faraway places, they are collecting messages from ancient times. The universe becomes a kind of archive, written not on paper but in starlight, stretched across distances so vast that ordinary words start to feel a bit underdressed. This is why the question of what lies beyond the observable universe is so subtle. It is not asking what lies beyond the universe itself, at least not at first. It is asking what lies beyond our cosmic line of sight. Imagine standing in the middle of a foggy field. You can see a certain distance in every direction. Beyond that, the field continues, perhaps with trees, fences, sheep, and one person wondering why they came out in slippers, but you cannot see it because the fog blocks your view. The edge of your visible world is not the edge of the field. It is just the edge of what the conditions allow you to observe. The observable universe is similar, though the fog in this case is not weather. It is the combined effect of distance, the speed of light, the age of the universe, and the way space itself has expanded over time. We are not trapped in a small universe. We are limited to seeing a certain portion of a much greater whole. At the centre of this observable region is not a special cosmic throne with Earth sitting proudly on it, though one can see why our ancestors might have liked that idea. We appear to be at the centre of the observable universe because observation always works that way. Wherever you are, the part of the universe you can see forms a sphere around you. If there were an astronomer in a distant galaxy billions of light years away, their observable universe would be centred on them. They would see some regions we cannot see, and we would see some regions they cannot see. Neither of us would be at the true centre of everything, assuming such a centre even exists. We would simply each be at the centre of our own view. This is a useful thing to remember, especially for humans, who are very good at accidentally placing themselves in the middle of the story. Cosmology has spent several centuries gently reminding us that we are not in the centre. They're not in a special galaxy. They're not even made of the most common kind of stuff, which is a lot of demotion for one species to absorb. Still, there is something comforting in it. We may not be central, but we are participants. We are inside the universe made from its materials, using little pieces of it to wonder about the rest. The distance to the edge of the observable universe can be confusing because the universe has not been sitting still while light crossed it. The universe is about 13.8 billion years old, but the farthest regions we can observe are now much farther away than 13.8 billion light years. That is because space itself has expanded while the light was travelling. A photon may have started its journey from a region that was once much closer, but during its long crossing, the space between there and here stretched. By the time that light reaches our telescopes, the place it came from is now far beyond the distance one might first expect. This is one of those facts that makes the universe feel less like a tidy room and more like a loaf of raisin bread expanding in the oven. The raisins are galaxies, the dough is space, and everyone involved is getting farther apart while smelling faintly of breakfast. It is not that galaxies are flying through space away from a central explosion, like fragments from a firework. Rather, space itself is growing, and as it grows, the distances between faraway galaxies increase. This expansion is one of the key reasons there can be regions beyond our observation. Light needs time to travel, but space is stretching as it does so. Some light from very distant regions has not reached us yet. Some may reach us in the far future. Some may never reach us at all, because the space between us and those regions is expanding too quickly for their light ever to cross the growing gap. That does not mean they are moving through space faster than light in a local sense. It means the space between us is increasing. This distinction matters because in relativity, nothing can travel through space faster than light, but space itself is not quite bound by the same everyday intuition. It can expand in a way that carries distant regions away from one another faster than light could bridge. That sounds like a loophole, and in a way, the universe is rather fond of loopholes, provided they are written into the geometry of reality. So what do we actually see when we look as far as we can? We do not see stars and galaxies all the way to the very beginning. The early universe was once hot, dense, and filled with charged particles that scattered light constantly. It was not transparent. Light could not travel freely through it, much as a lamp cannot shine clearly through thick soup, especially if the soup is being stirred by the entire cosmos. Only after the universe cooled enough for atoms to form did light begin to move freely across space. That ancient light still reaches us today as the cosmic microwave background. It is a faint afterglow from a time when the universe became transparent, a kind of baby picture of the cosmos, though admittedly one that requires radio telescopes, careful analysis, and a tolerance for grainy temperature maps. It comes to us from every direction, forming the oldest light we can directly observe. Beyond that surface we cannot see using ordinary light, because before that time the universe was opaque. The cosmic microwave background is not the edge of existence, it is the edge of direct vision. This is important because it tells us that even within the observable universe, there are limits to how directly we can look. The universe hides its earliest moments not because it is being rude, but because the conditions then were different. To study those earlier times, scientists use indirect clues. They look at patterns in the cosmic microwave background, the distribution of galaxies, the abundance of light elements, and the behaviour of space itself. It is rather like trying to understand a cake by studying the crumbs, the smell in the kitchen, the oven temperature, and the expression of the person who says they definitely followed the recipe. We cannot watch the very first moments with a telescope in the usual way, but we can infer a remarkable amount from what those moments left behind. Now, beyond the observable universe, the simplest possibility is also the most likely sounding one. There may simply be more universe. More space, more galaxies, more clusters, more cosmic voids, more ancient light heading toward places that are not us. If the universe is large enough, then our observable region may be just a small patch within a much greater cosmic landscape. In that case, going beyond what we can see would not mean crossing into a different realm. It would be more like sailing beyond the visible horizon on Earth. From the shore, the ocean seems to end where the sky touches the water, but of course it continues. The horizon is not a wall, it is a limit set by your viewpoint. A ship disappearing over it has not fallen out of reality. It has simply moved beyond your line of sight, which is reassuring for both sailors and cosmologists. But there is a difference between earthly horizons and cosmic ones. On Earth, you can travel toward the horizon, and although it keeps moving away as horizons tend to do, you can at least reach the places that once lay beyond it. In cosmology, the situation is harder. Because the universe is expanding, some regions beyond our observable horizon may be permanently unreachable, not just by spacecraft, but by information of any kind. Their light will never arrive. Our light will never arrive there. No message can pass between us. They are not merely far away, they are causally disconnected from us. This is a rather formal way of saying that the universe may contain places that are real, but forever outside our ability to affect or observe. They may be part of the same universe, governed by the same broad laws, filled with stars and galaxies, perhaps even planets and curious beings of their own, but they are sealed away from us by the expansion of space. Somewhere beyond our horizon, there may be light from galaxies that will shine forever without ever entering our sky. That thought can feel lonely at first, but it is also a reminder that the universe is not designed around our access to it. It does not promise to be fully visible. Science is often described as the search for knowledge, but it is also the careful mapping of limits. We learn not only what we can know, but why some things may remain hidden. This does not make the hidden regions meaningless. It makes them part of the structure of the question. To ask what is beyond the observable universe is to stand at the boundary between evidence and possibility, between what telescopes can show and what theory can reasonably suggest. It is a place where scientists must be disciplined, because imagination is very eager to run ahead, usually without packing sensible shoes. The best scientific answer begins with what we can measure from our own observable patch. On very large scales, the universe appears remarkably uniform. Galaxies are not spread evenly on small scales. They gather into clusters, threads, walls, and enormous empty regions called voids. The cosmic web has structure, and it is beautiful in the way that only something unimaginably huge and faintly spider-like can be. But when we zoom out far enough, the universe looks broadly similar in every direction. This large-scale smoothness suggests that our observable region may be typical of a larger universe. If that is true, then beyond our horizon there is probably more of the same, at least for some great distance. More cosmic web, more matter, more dark matter shaping galaxies, more dark energy influencing expansion, more regions where stars have formed, burned, exploded and seeded space with heavier elements. This does not mean every place is identical. It means the overall pattern may continue, There is a quiet power in that idea. The observable universe already contains hundreds of billions of galaxies, each with billions of stars. It is so large that the mind tends to turn it into a simple word and move on, because actually trying to picture it is like trying to count every raindrop in a storm while also making a sandwich. Yet this immense region may be just a sample. The full universe could be far larger. It could even be infinite. If it is infinite, then beyond what we see there is not just more space, but endlessly more space, stretching without boundary. Infinity is a tricky idea, and not one to toss around casually, like glitter at a school craft table. In physics, saying the universe might be infinite does not mean we know it is. It means current observations are consistent with a universe that may be spatially flat and possibly without end. But even if the universe is finite, it could still be vastly larger than the observable part. A finite universe can be unbounded in certain geometries, just as the surface of Earth has no edge even though it has a finite area. If you walk in one direction long enough on Earth, ignoring oceans, mountains, private property, and the need for snacks, you do not reach an edge. You eventually return to where you began. Space itself might have shapes that are difficult to picture because our brains evolved to navigate forests, not higher dimensional cosmic geometry. This is where the question begins to widen. Beyond the observable universe might be more of our universe, perhaps much more. But depending on how the early universe behaved, there may be regions so far beyond our horizon that they developed with different conditions. There may be variations in the distribution of matter, different histories of galaxy formation, or in some speculative ideas, even different physical properties. Some theories suggest that what we call the universe could be one region within a much larger structure produced by cosmic inflation, the extremely rapid expansion thought to have occurred very early in cosmic history. Inflation was originally proposed to explain why the observable universe is so smooth and why its geometry appears so close to flat. It also has a curious consequence in many models. Once inflation starts, it may not stop everywhere at once. Some regions stop inflating and form universes like ours, while other regions keep inflating, potentially producing more regions. This leads to the idea of a much larger multiverse, not in the casual movie sense of meeting another version of yourself with better hair, but in the cosmological sense of separate regions of space, with different histories, forever beyond direct contact. We will move carefully with that idea, because it is fascinating but also speculative. It sits at the edge of what science can currently test. Still, it grows out of serious attempts to understand the early universe, not simply out of a desire to make reality more dramatic. The trouble is that anything beyond our observable horizon is by definition hard to observe. We can look for indirect signs. We can study whether our observable universe carries clues of collisions with other regions, or whether its large-scale patterns reveal something about what lies beyond. So far, the evidence does not give us a clear window. The curtain remains mostly closed. But the fact that we cannot see beyond it does not mean there is nothing there. It means our methods must be patient, precise, and honest about uncertainty. And uncertainty in this case is not a failure. It is part of the wonder. The universe we can see is already enough to fill a lifetime of study, and yet it may be only the visible room of a much larger house. We stand inside that room with instruments built from metal, glass, silicon, and mathematics, listening for faint signals from the earliest light. We map galaxies. We measure expansion. We compare theories against the sky. We do not know everything beyond the observable universe, but we know why the question exists, and we know the boundary is not a simple edge. It is a horizon created by time, distance, and expansion. It is the place where light has not yet reached us, or perhaps never will. It is not the end of the universe. It is the end of our current view. So as we begin this slow journey outward, it may help to keep one image in mind. Picture yourself standing in a wide, dark field at night, holding a lantern. The lantern reveals grass, stones, perhaps a path just ahead. Beyond the glow, the field continues, but you cannot see its shape. You can make careful guesses from the ground beneath your feet, from the slope of the land, from sounds in the distance, from the way the wind moves. You would be wrong to claim the field ends where the light fades. You would also be wrong to claim you know every tree and hill beyond it. The honest answer lies between those extremes. There is more beyond the glow, and the task is to understand what the glow itself can tell us. In cosmology, our lantern is the observable universe. Its light reaches us from every direction, ancient and stretched and full of clues. And as we look outward, deeper into the sky and farther back in time, we begin to understand that the edge we talk about is not a border around reality, but a reminder of how vast reality may be beyond the reach of even our oldest light. When we talk about the edge of the observable universe, it is tempting to picture something sharp and distant, like a cliff at the end of all space, a place where galaxies thin out, the stars become fewer, and then, perhaps after one last lonely nebula, reality simply stops, as if the universe were a stage set and someone forgot to paint the scenery beyond the curtain. But the edge we cannot see is not that sort of edge. It is not a border. It is not a wall. It is not a cosmic fence with a small sign saying please do not lean on the fabric of space. It is much stranger than that, and much more ordinary at the same time. It is a limit created by the fact that light takes time to travel, and the universe has only been around for a finite amount of time. We see as far as messages have had time to reach us. Beyond that, there may be more space, more galaxies, more darkness filled with distant stars, but the light from those places has not arrived here. It may arrive one day from some regions. From others, because of cosmic expansion, it may never arrive at all. That is the first important thing to hold gently in mind. The edge of the observable universe is not the edge of the universe. It is the edge of our information. It is the place where our view runs out. Imagine standing on a hill in the early morning with mist lying across the fields. You can see the nearest trees, perhaps a lane, perhaps the roof of a farmhouse, and then the world fades into grey. You would not say the countryside ends where the mist begins. You would say that is simply as far as you can see right now. The universe gives us a similar situation, though instead of mist we're dealing with time, distance, expansion, and light that has been stretched into faint ancient signals. The view fades not because space becomes empty, but because there has not been enough cosmic time for everything to announce itself to us. This can be a little difficult, because our everyday idea of seeing is so immediate. You open your eyes, and the room appears. The lamp, the chair, the cup of tea you were quite sure you placed farther from the edge of the table. It all seems to arrive at once, but even in a room, sight is not instant. Light is travelling from objects to your eyes. The distance is so small and light is so fast that the delay is completely unnoticeable, unless you have the reflexes of a laboratory instrument and possibly the social life of one too. Across space, however, the delay becomes everything. The moon is seen not as it is right now, but as it was just over a second ago. The sun is seen as it was several minutes ago. The nearest stars are seen as they were years ago. A galaxy across deep space is seen as it was when Earth was younger, before humans, before mammals, before familiar continents had arranged themselves into their present shapes. To look outward is to look backward, and this makes the sky a kind of time machine, though sadly one without comfortable seats or snacks. The farthest edge we can observe is therefore also the oldest light we can receive. But even that sentence needs some care, because when we look very far away, we're not looking at galaxies as they exist now, we are looking at the light they sent long ago. Some of those galaxies may have changed beyond recognition. Their stars may have aged. Their shapes may have shifted. They may have merged with other galaxies. Some of the stars whose light we collect may no longer exist. The universe we see in deep images is not a single present moment spread across space. It is a layered record of different ages, Nearby objects show us the recent universe. Farther objects show us an older universe. The most distant light shows us the universe when it was very young indeed. If the cosmos were a family album, the pages would not be arranged neatly by year. They would be stacked in every direction at once, and every telescope would be a way of reading time by distance. At the limit of ordinary sight, we do not see the beginning itself. We see a glow left over from a time when the universe became transparent. Before that, the universe was filled with hot charged particles that scattered light constantly. Photons could not travel freely across great distances. They bumped and scattered and wandered, trapped in a bright dense fog. Then the universe expanded and cooled enough for atoms to form. Once electrons and nuclei joined into neutral atoms, light could move freely. That first freely travelling light has crossed the universe ever since, stretched by expansion into microwaves. Today it surrounds us from every direction as a faint background signal. It is often described as the afterglow of the early universe, and it marks a kind of visual boundary. Not because nothing existed before it, but because earlier than that, light could not carry a clear picture to us. So the edge we cannot see has more than one meaning. There is the farthest light we can receive. There is the surface beyond which the early universe was opaque to ordinary light. There are regions farther away whose light has not yet had time to reach us. And there are regions whose light may never reach us because space between us and them is expanding too quickly. These are not all the same edge, which is why cosmology can sometimes feel like asking for directions and being told there are 4 horizons, 2 kinds of distance, and one of them depends on what you mean by now. But the idea beneath it is simple enough. Our view is limited, and those limits come from the behaviour of light and space. The word horizon is helpful here. On Earth, a horizon is not a physical thing. It is not lying out there in the distance waiting to be collected and put in a drawer. It depends on where you stand. Move higher and you see farther. Move somewhere else and the horizon changes. The cosmic horizon is similar in spirit, though much grander and less likely to involve sheep. We sit at the centre of our observable universe, because every observer sits at the centre of what they can observe. If you were in a galaxy far away, your cosmic horizon would be centred on you. You would see some regions hidden from Earth, and Earth would see some regions hidden from you. There is no special central point being granted a privileged view. There are only observers, each surrounded by the sphere of light that has had time to reach them. This is a useful correction to a very natural misunderstanding. When diagrams show the observable universe as a sphere, with us at the centre, it can look as though Earth occupies the middle of everything. But that is not what the picture means. It means our observations spread outward equally in every direction, or nearly enough for the purposes of a simple diagram. It is the same way a person standing in a dark field with a lantern appears to be at the centre of a circle of light. The circle is centred on them not because the field was built around them, but because the lantern is theirs. Our telescopes are the lantern. The light reaching us is the illuminated circle. The field may go on far beyond it. This idea asks for a bit of humility, which science has been handing to humanity in generous portions for centuries. First we learned that Earth is not the centre of the solar system, then that the Sun is just one star among many, then that the Milky Way is just one galaxy among many. Now we understand that even the entire observable universe may not be the whole universe. It may be a local patch, a very large patch of course. So large that calling it local feels a bit like calling the ocean a puddle, because you happen to be standing beside a larger ocean. But in cosmological terms, it may still be only part of the full picture. The scale of this possibility is difficult to absorb. The mind tries to stretch, gives a brave little creak, and then quietly asks whether we might discuss something smaller, like a galaxy cluster or a complicated wardrobe. To understand why the edge is invisible, we also need to remember that space is not a still container. It is expanding. Distant galaxies are not simply moving through space in the same way a boat moves across a lake. On the larger scales, the space between galaxies is growing. This means that while light is travelling toward us, the distance it must cross can increase. A beam of light from a distant galaxy may make steady progress locally, moving at the speed light always moves, but the fabric of space between the galaxy and us is stretching during the journey. For nearby galaxies, this stretching is not enough to prevent the light from reaching us. For very distant regions, it changes the story completely. Some light has been travelling for billions of years and is only now arriving. Other light is on its way but will not arrive for an unimaginably long time. And some light, from regions beyond a certain cosmic limit, will never reach us, no matter how long we wait. The universe is not merely large. It is growing in a way that can place regions permanently beyond one another. This can sound unsettling, as if the cosmos is slowly taking things away from us. In a sense, it is. Over very long times, distant galaxies will become harder to see as expansion carries them farther away and stretches their light more and more. Galaxies outside our local gravitational neighbourhood will fade from view, not because they switch off, but because their light becomes too stretched and too faint to detect. Far in the future, astronomers in whatever remains of our galaxy may look out and see a much emptier sky. They may not have easy evidence of the vast cosmic web we see today. They might live in a universe that appears like an island of stars surrounded by darkness, unaware of the countless galaxies that once filled the observable sky. That is a strange thought. We happen to live at a time when the universe is old enough to have formed galaxies and stars and planets, but young enough that distant cosmic history is still visible. We are late enough to look back, but not so late that the view has vanished. There is something almost practical about this, like arriving at a scenic overlook before the fog rolls in. The universe has given us a window, and astronomy is the act of looking through it while we can. Every deep sky survey, every map of distant galaxies, every measurement of ancient light is part of preserving the evidence of a cosmos that will not always be equally available to observers. This does not mean we should panic and start taking photographs of every galaxy immediately, though astronomers are, in their own calm and data-heavy way, doing exactly that. It means that our place in cosmic time matters. We are not just located somewhere in space, we are located somewhere in history. The edge we cannot see is shaped by both. It is also important to ask what we mean by cannot see. In science, seeing does not always mean seeing with human eyes. We use radio waves, infrared light, ultraviolet light, X-rays, gamma rays, neutrinos, gravitational waves, and every other messenger nature allows us to detect. Each messenger reveals a different layer of reality. Dust that blocks visible light may glow in infrared. Violent events may reveal themselves through high-energy radiation. Merging black holes can send ripples through space itself. So when cosmologists say a region is beyond the observable universe, they do not mean beyond what a person could see if given a very large telescope and perhaps a ladder. They mean beyond the reach of any signal that could have arrived here by now. No light, no particle, no gravitational whisper. Nothing from that region has had time to touch us. It is beyond causal contact. Causal contact is one of those phrases that sounds technical but expresses a simple idea. Two places are in causal contact if something from one could have influenced the other. A flash of light, a gravitational effect, a particle, a message, a very ambitious postcard. If no signal can pass between two regions, then they cannot affect one another. They may both exist within a larger universe, but from each other perspective they are sealed away. We can talk about them only through theory and inference. This is where the edge becomes not just a limit of sight, but a limit of connection. It is not merely that we do not know what is there. It is that there may be no possible experiment that lets us receive information from there directly, at least according to our current understanding. That sounds final, but science has a way of being careful with final words. There may be indirect clues about what lies beyond our horizon. The universe we observe carries patterns. The distribution of galaxies, the slight variations in the cosmic microwave background, the overall geometry of space, and the rate of expansion all give hints about the larger reality. If our visible region is smooth and uniform on very large scales, that suggests the region beyond may also continue in a similar way, at least for some distance. If space appears flat as far as we can measure, that may suggest the universe is much larger than the part we see, perhaps even infinite. But these are conclusions drawn from evidence inside our horizon. We cannot simply point a telescope beyond it and check. The best we can do is study the visible patch so well that it tells us something about the hidden landscape. This is not unusual in science. Much of science involves learning about things we cannot see directly. We infer the interior of Earth from seismic waves. We infer the existence of dark matter from its gravitational effects. We infer the lives of extinct animals from bones, footprints, and the occasional fossil that looks as though nature was trying to make a point. The unseen is not automatically unknowable, but the farther we move from direct evidence, the more careful we must be. Beyond the observable universe, there is room for solid inference, cautious possibility, and speculation. Good cosmology tries not to mix them up, though the human imagination is always very keen to help, usually by arriving early and rearranging the furniture. One of the most reasonable expectations is that beyond our view, there is more of the same kind of universe. This expectation comes from the cosmological principle, the idea that on sufficiently large scales the universe is roughly the same everywhere and in every direction. This principle is not just a guess made because scientists enjoy symmetry, though they often do. It is supported by observations showing that the universe looks broadly uniform when viewed on very large scales. There are galaxies and clusters and voids, yes, but the overall distribution smooths out. The cosmic microwave background is also remarkably even, with only tiny variations. These variations are extremely important because they grew into the large-scale structure we see today, but the overall smoothness is striking. If our region is typical, then beyond the observable edge there should be more cosmic web, more galaxies, more great dark spaces between them, more stars forming and dying, more ordinary matter, dark matter, and dark energy doing their quiet, complicated work. Still, typical does not mean identical. If you look out your window and see one stretch of countryside, you might reasonably infer that the landscape continues beyond the hill, but you would not expect every tree to repeat in the same place, every pond to have the same shape, and every cow to look equally surprised. Beyond our cosmic horizon, the universe may have the same overall character, while still containing different structures, different galaxy arrangements, and histories we will never know. There may be galaxy clusters larger than any we see, voids wider than any we have mapped, and countless worlds under skies whose light will never enter ours. If life exists elsewhere beyond our horizon, those beings may have their own observable universe, their own cosmic microwave background, their own version of the question. They might wonder what lies beyond their visible limit, never knowing that somewhere far outside their reach, on a small rocky planet, another species has misplaced its socks while asking the same thing. This is one of the quieter wonders of the subject. The edge we cannot see is not only a scientific boundary, it is a reminder of how local every perspective is. We often speak as though the universe is what we observe, but observation is always from somewhere. Our cosmic view is shaped by our location and by the age of the cosmos when we happen to be looking. We do not see the universe from the outside. There is no balcony seat. We are embedded within it. We infer the whole from the part, like trying to understand an entire symphony by hearing the notes that can reach one chair in the concert hall. Fortunately, the universe has left us a very rich set of notes. They are faint, stretched, scattered across the sky, and often require instruments with names that sound like they were assembled by committees, but they are there. The edge we cannot see also changes how we think about distance. In daily life, distance is something you could, in principle, cross. A far mountain is difficult to reach, but not conceptually mysterious. A distant city may require a train, a plane, or a heroic tolerance for motorway service stations, but it belongs to the same accessible world. Cosmic distance is different. Some places are not just far in practice, they are beyond reach in principle, because the expansion of space prevents any signal from crossing the gap. A galaxy beyond a certain horizon is not merely inconveniently distant, it is unavailable to us forever, unless our understanding of physics changes in some deep way. This gives cosmology a particular flavour of wonder. It is not the wonder of a treasure map where every blank spot might one day be filled in. It is the wonder of knowing that some blank spots may remain blank, not because we lacked curiosity, but because reality has horizons built into it. And yet those horizons do not make the universe feel smaller, they make it feel larger. A wall would make the universe smaller. A horizon suggests continuation. It says the visible world is not all there is. It says our maps end before reality does. That is a comforting thought in its own odd way. The unknown is not necessarily an emptiness. It may be abundance beyond reach, more space than we can measure, more history than we can receive, more light travelling forever toward observers that are not us. The edge is not a place where the universe runs out. It is where our particular story of receiving light runs out. As we rest with that idea, the night sky becomes a little different. The darkness between stars is not simply blank. Some of it is nearby darkness, the ordinary absence of bright objects in a given direction. Some of it is ancient darkness, filled with light too faint or too stretched for our eyes. Some of it is darkness from beyond any signal we have yet received. When you look up, you are not looking at a ceiling. You are looking into a layered history, with every direction carrying a mixture of presence and delay. The edge we cannot see is not somewhere straight ahead. It surrounds us. In every direction, if we look far enough, we meet the limit of what has been able to arrive. And just beyond that limit, the universe may continue, quiet and unreachable, carrying on without needing to be seen. This brings us naturally to the next part of the journey, because the edge of our view is made by light, and light is the messenger that turns distance into history. To understand why the observable universe has the size it does, and why looking outward means looking into the past, we need to follow that messenger more closely. We need to think about the long road light travels, how it stretches as space expands, and how the oldest signals in the sky tell us not just where things are but when they were. To understand why there is an edge to what we can observe, we have to spend a little time with the universe's most reliable messenger, light. Light is how the cosmos tells us where things are, what they are made of, how hot they are, how fast they are moving, and, in a very real sense, when they are. It is easy to think of light as something that simply reveals the world, the way a lamp reveals a room after you switch it on. But across the universe, light does much more than that. It carries history. Every beam of light that reaches us from space has been travelling for some length of time, and the farther away its source, the older the message. So when we look into the distance, we're not seeing a single cosmic present. We are seeing layers of the past stacked outward in every direction. The nearest things show us recent moments. The farther things show us older moments. The most distant light we can collect shows us the universe as it was when it was young, hot, and still learning how to become transparent. This is one of the most important ideas in astronomy, and also one of the gentlest. The night sky is not a photograph of how everything is right now. It is a collection of delayed arrivals. The moon we see is the moon from just over a second ago. That delay is tiny, but it is real. The sun we see is the sun from several minutes ago, which means sunrise is always a little bit late, though no one has yet managed to complain to the management. When we look at the nearest stars, we are seeing light that began its journey years ago. When we look at nearby galaxies, the delay grows to millions of years. When we look at the most distant galaxies, we are seeing light that started travelling before Earth had flowers, before animals walked on land, before the sun had even completed many of its long loops around the Milky Way. Space does not just separate places, it separates moments. The reason is that light, while extremely fast, is not instant. In everyday life, it might as well be. If someone turns on a lamp across the room, you do not sit there waiting politely for the light to arrive. It reaches you so quickly that your brain treats it as immediate. But the universe is not a room. It is not even a very large room, though if it were, someone would definitely have lost the remote control in it by now. Across cosmic distances, even light needs time. This turns astronomy into a kind of archaeology, except the fossils are made of radiation, and the excavation site is the entire sky. Astronomers collect ancient light and use it to reconstruct the history of the universe. They do not need to travel back in time. The past is already arriving one faint photon at a time. A useful way to think about this is to imagine receiving letters from distant places. A letter from the next town might tell you what happened yesterday. A letter from across the ocean might tell you what happened weeks ago. A letter from a ship slowly crossing the world might tell you news from months in the past. Now imagine that every object in the sky is sending letters, but the letters travel at the speed of light, and the distances are so enormous that some take billions of years to arrive. A telescope is not just a magnifying glass, it is a mailbox for ancient messages. When astronomers study a distant galaxy, they are reading a letter written when that galaxy was younger. The galaxy may no longer look the same today. It may have merged with another galaxy. Its stars may have aged. Its bright blue regions of star formation may have dimmed. But the light we receive preserves what it was like when the message was sent. This is why distance and age are tied together in cosmology. A faraway galaxy is not simply far away in space, it is far away in time. The deeper we look, the earlier the universe becomes. This sounds simple, but it carries a strange consequence. We cannot build a perfect map of the universe as it exists right now, because information from distant regions has not reached us yet. We can only map what those regions looked like when their light began travelling. For nearby space, the difference is small enough to ignore in many cases. For the deep universe, the difference is everything. A galaxy seen across billions of years of light travel time is not a current neighbour. It is an ancestor of whatever exists in that region now. This is one of the reasons deep space images can feel so powerful. When you look at a field of distant galaxies, you're not just seeing many places, you're seeing many ages. Some galaxies in the image may be relatively nearby, as cosmic things go. Others may be so distant that their light has crossed most of cosmic history to reach us. The image becomes a layered view through time. It is like looking down a long city street where each building belongs to a different century, except the street is expanding, the buildings are galaxies, and the street lamps are powered by nuclear fusion. A bit inconvenient for city planning, but excellent for cosmology. As light travels through the expanding universe, something else happens to it. It stretches. This stretching is called redshift, because visible light shifted toward longer wavelengths moves toward the red side of the spectrum. If the stretching continues beyond visible light, it can move into infrared, microwave, and radio wavelengths. The name comes from visible colour, but the idea applies across all kinds of light. The important point is that space itself expands while the light is travelling, and as space stretches, the light travelling through it stretches too. By measuring how much the light from a distant galaxy has been stretched, astronomers can estimate how much the universe has expanded since that light was emitted. That makes redshift one of the great tools of cosmology. It tells us not only that a galaxy is distant, but also that we are seeing it from an earlier time in the universe's history. There is a common comparison that helps, though it is a little homely for such a cosmic subject. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because the dots are crawling across the rubber, but because the surface between them is stretching. If a tiny wave were drawn between the dots, it would stretch too. The universe is not exactly a balloon, and space is not rubber, and no one should try to inflate a universe at home without supervision, but the image gives the right feeling. Light crossing expanding space is stretched by the expansion. By the time it reaches us, its colour carries the imprint of the journey. This stretching matters especially for the oldest light in the universe, the cosmic microwave background. Long ago, the universe was not transparent. It was filled with hot charged particles, and light could not travel freely. Photons were constantly scattered, bounced around by free electrons, unable to move in straight lines for long. The universe was bright, but not see-through. It was more like a glowing fog than an open sky. Then, as space expanded, the universe cooled. Eventually it cooled enough for electrons and atomic nuclei to join into neutral atoms. Once that happened, light was no longer scattered so strongly. It could finally travel freely. That ancient light has been travelling ever since. When it was first released, that light would not have looked like the faint microwave glow we detect today. It came from a hot young universe, and its wavelengths were much shorter. But over billions of years, the expansion of space stretched it enormously. Today it reaches us as microwaves, faint and cold, arriving from every direction. It is not light from stars, it is older than stars. It is not light from galaxies, it is older than galaxies. It is a leftover glow from the time when the universe first became transparent. This makes it one of the most valuable signals in all of science. It is a direct view of the early universe, not at the absolute beginning, but from a time close enough to the beginning that it carries clues about what came before. The cosmic microwave background is sometimes described as the oldest light we can see. That is true in an important sense, but it is worth being precise. It is the oldest light that has travelled freely to us. Before the universe became transparent, light existed, but it could not move across space in a way that preserved a clear image. If you try to look farther back with ordinary light, you would run into that opaque early phase, like trying to see through a thick curtain. The curtain is not the beginning of the universe. It is the point beyond which ordinary light cannot give us a direct picture. To study earlier times, cosmologists have to rely on indirect evidence and other kinds of messengers, such as patterns in that background glow, the abundance of early elements, and the gravitational imprint of the universe's first conditions. The cosmic microwave background is remarkably smooth. If you measure its temperature across the sky, it is almost the same in every direction. That smoothness tells us that the early universe was extremely uniform. But almost is the important word. There are tiny variations, very small differences from place to place. These tiny variations are not random decoration, they are the seeds of cosmic structure. Over time, gravity amplified them. Slightly denser regions pulled in more matter. Matter gathered into larger clumps. Those clumps became the first stars, galaxies, clusters, and eventually the vast cosmic web. In that faint ancient glow, we can see the beginnings of the structure that later became everything familiar in the night sky. It is rather like looking at a very plain bowl of batter and somehow seeing the future cake, though in this case the cake includes galaxies, planets, and someone forgetting where they put their reading glasses. After the universe became transparent, there was a long period often called the cosmic dark ages. This does not mean the universe was empty. Matter was there. Dark matter was there. Hydrogen and helium filled space. But stars had not yet formed, so there were no bright points of light in the way we think of the night sky today. The universe was transparent but mostly dark. Slowly, gravity worked on those tiny density variations. Gas collected in the deepest gravitational wells. The first stars ignited. These first stars were likely very different from many stars today. They formed from the simplest ingredients, mostly hydrogen and helium, without the heavier elements that later generations of stars would produce. They were probably massive, brilliant, and short-lived. They burned hot and died dramatically, spreading the first heavier elements into space. Those first stars changed everything. They lit up the darkness. They began the long process of enriching the universe with carbon, oxygen, iron, and the other elements needed for planets, chemistry, and eventually living things. They also began to transform the gas around them, sending out energetic light that changed the state of matter across intergalactic space. This era, when the first stars and galaxies began to light and reshape the universe, is one of the great frontiers of modern astronomy. We are trying to observe the earliest galaxies, not because they are pretty, though many are in a faint smudgy way, but because they show us how the universe moved from simplicity to structure. They are the first signs of the cosmic web waking up. Seeing these earliest galaxies is difficult because their light is extremely faint and extremely stretched. By the time it reaches us, much of it has shifted into infrared wavelengths. This is one reason infrared telescopes are so important. They allow astronomers to study light from objects so distant that visible light has been stretched beyond the range our eyes can detect. A telescope like the James Webb Space Telescope was designed in part to study this ancient infrared light. It can look for some of the earliest galaxies, study their shapes, estimate their ages, and examine the light from their stars and gas. It is not looking at the edge of the universe in the sense of a wall. It is looking back toward the time when the first galaxies were forming. It is collecting clues from the universe's childhood. But there is a subtle point here. When we say a telescope sees a galaxy from the early universe, that galaxy is not located near some outer rim. It only appears in that ancient state because its light took so long to reach us. A distant galaxy is not physically sitting next to the beginning of time. It is simply so far away that we see it as it was long ago. If there are observers in that galaxy today, assuming the galaxy still exists in some evolved form and has planets and observers, and perhaps someone also staring into the sky instead of sleeping, they would see their local surroundings as modern, not ancient. They might look toward the Milky Way and see our region as it was billions of years ago. Everyone sees distant regions in the past. No one gets a live broadcast of the whole universe. This is another reason the idea of a cosmic edge can mislead us. The farthest visible regions are not places at the edge of a sphere in an absolute sense. They are the oldest visible layers in our past light cone. That phrase sounds technical, but the idea is manageable. Everything we see is part of the set of light signals that have arrived at our location by now. Nearby signals left recently. Distant signals left long ago. The farther out we look, the deeper down this cone of past light we're seeing. Our view is shaped not only like space, but like history. We are always looking backward along paths that light has travelled. This also means that the observable universe is not static. As time passes, light from more distant regions has more time to arrive. In that sense, our observable universe can grow. We may receive signals tomorrow that had not quite reached us today, though on human timescales the change is not exactly dramatic. It is not like the universe sends a new galaxy every morning with the post. On cosmic timescales, however, the situation is complicated by expansion. Some regions become newly observable as their light arrives, while other regions are carried beyond horizons that prevent any future signals from reaching us. The observable universe is a balance between time passing and space expanding. It is not a fixed bubble painted on reality. It is an evolving relationship between us and the rest of the cosmos. The age of the universe gives us one limit, but expansion reshapes it. The oldest light we receive has been travelling for almost the entire age of the universe, yet the region that emitted it is now much farther away than a simple travel time would suggest. This is because the space between us and that region expanded during the journey. So if someone asks how far away the source of the cosmic microwave background is, the answer depends on what kind of distance you mean. There is the time the light has travelled. There is the distance to the region when the light was emitted. There is the distance to that region now. Cosmology has to define distance carefully, because the universe does not keep still while we measure it. It is rather like trying to measure the length of a loaf of bread while it's rising, except the loaf is space itself, and the raisins are galaxies quietly drifting apart. This expanding distance does not mean light is failing at its job. Light always travels locally at its own speed. But across the larger scales, the geometry of space determines what paths are possible and how those paths change. Some light emitted long ago by distant regions can reach us now. Some light emitted today from very distant regions may never reach us. There are galaxies we can see as they were in the past, but from which we will never receive light emitted in their present. We can observe their youth, but not their adulthood. In a way, the universe lets us read certain old letters from places that can no longer send new ones. That is a rather strange kind of relationship. We know they were there, we can study what they were like, but their later story may be permanently hidden. The ancient universe also teaches us that the farther we look, the less familiar things become. Nearby galaxies include grand spirals, giant ellipticals, irregular dwarfs, and many forms shaped by long histories of star formation and mergers. Farther back, galaxies tend to look smaller, clumpier, more chaotic. They are still assembling. Their stars are younger. Their gas is more active. Heavy elements are less abundant. Looking deep into space is like looking through a sequence of cosmic adolescence, childhood and infancy, though galaxies, unlike teenagers, do not leave plates in their rooms. The universe has changed over time. It did not begin filled with mature galaxies, it grew them. It built complexity step by step through gravity, nuclear fusion, stellar death, and the slow gathering of matter into structure. This matters for our main question because the observable universe is not just a region, it is a history we can see. The edge we cannot see is not merely beyond a distance, it is beyond the oldest signals that can reach us. When we ask what lies beyond the observable universe, we're asking what exists outside our accessible history. There may be regions whose light has not arrived. There may be regions whose light never will. There may be early conditions whose direct light cannot pass through the opaque beginning. Each limit is connected to the way light travels through a changing universe. And yet, even with these limits, light has given us an extraordinary amount. It tells us that the universe expanded from a hotter, denser state. It tells us that atoms formed early, that the first light travelled freely, that gravity shaped tiny variations into galaxies, that stars produced heavier elements, that galaxies gathered into a web, and that expansion continues today. Every telescope image is part of that larger story. Every spectrum, every faint dot, every background glow is a clue. The universe may hide what lies beyond our horizon, but it has not been silent. It has been sending messages since it became able to send them. So when we look at the night sky, it may help to think of the darkness not as empty distance, but as depth. Some of that depth is filled with nearby stars. Some contains galaxies whose light left before humans existed. Some reaches back to the first billion years of cosmic history. Some ends at the ancient glow of the transparent universe. Beyond that, ordinary light gives way to inference, and beyond our horizon, even inference must become careful and modest. The sky is not a flat backdrop. It is a record of travel times. It is a history written in light that has crossed expanding space to reach one small planet at this particular moment. From here, the next step is to picture the observable universe itself, not as the whole of reality, but as the bubble of information around us. It has a size, a shape from our perspective, a history contained within it, and a boundary that follows us wherever we are. It includes every galaxy we can ever hope to study directly from Earth, every ancient glow that has reached us, and every clue we use to infer the larger universe beyond. Understanding that bubble helps us see why our cosmic home is both unimaginably vast and, in the larger sense, possibly only a small illuminated patch within something far greater. Now that we have followed light across distance and seen how the ancient universe reaches us as a delayed message, we can begin to picture the region those messages define. The observable universe is not the entire universe wrapped neatly in a label. It is the part of the universe that has managed to become known to us. It is our cosmic bubble of information, a sphere of visibility centered on Earth, not because Earth is important in the grand construction of reality, But because Earth is where we happen to be receiving the light, every observer has such a bubble. A patient astronomer in a galaxy 10 billion light-years away would not be sitting inside our observable universe in the same way we do. They would have their own, centered on their world, filled with a different arrangement of visible regions. Some of what we see would lie beyond their horizon, and some of what they see would lie beyond ours. So when we speak of the observable universe, we are not naming a special container built around us. We are naming the view from here. That view is still almost absurdly large. It contains every galaxy whose light has reached our telescopes, every ancient signal that has crossed space to arrive at our detectors, every patch of cosmic background glow we can measure, and every structure close enough in cosmic history to be connected to us by light or other signals. It includes the Milky Way, of course, with its spiral arms, star clouds, old globular clusters, black hole at the centre, and our small solar system tucked into one ordinary region, like a cottage somewhere off a country road. It includes our neighbouring galaxies, the Magellanic Clouds, Andromeda, and many smaller companions. It includes the local group, then clusters of galaxies, superclusters, filaments, walls, and enormous voids where galaxies are scarce. It stretches outward through a web of matter so vast that even the word vast begins to look a little tired and in need of a sit-down. And beyond all those galaxies, in every direction, it reaches back to the oldest light we can observe, the faint microwave afterglow from when the universe first became transparent. Calling it a bubble is useful, but we must be careful not to imagine a shiny soap bubble floating in a larger room. There is no known membrane around it. Nothing pops if a galaxy crosses the edge of our view, though cosmologists would certainly have questions if it did. The bubble is simply the region from which signals have reached us. Its boundary is made from time and light. It is not a surface in space that you could travel to and inspect. If you flew toward the edge, which would already be a rather ambitious afternoon, the edge would not sit still waiting for you. Your own observable universe would shift with you, always centered on your location. In that sense, the observable universe is less like a room and more like the circle of light cast by a lantern in a dark field. Move the lantern and the circle moves. The field itself may continue far beyond the glow. This can make diagrams of the universe misleading. We often see illustrations that place Earth or the Milky Way in the middle, surrounded by shells showing older and older times, with the cosmic microwave background around the outside. These diagrams are not saying that we are at the physical centre of everything. They are showing what we can see from our position. The outer shell represents the oldest light reaching us from all directions. If you move to another galaxy, you could draw the same kind of diagram around that galaxy. This is an important point, because the human imagination has a habit of turning viewpoints into privileges. We see ourselves in the middle of a picture and think, even for a second, that perhaps the universe has arranged itself around us. It has not. We are centered only in the sense that anyone holding a flashlight is centered in their own patch of light. The scale of this bubble can be difficult to describe without numbers, and even with numbers it remains difficult, because numbers that large tend to become decorative rather than meaningful. The light from the farthest visible regions has travelled for nearly the entire age of the universe, but because space has expanded during that journey, those regions are now much farther away than the travel time alone suggests. This is one of the reasons cosmological distance is not like measuring the length of a table, unless the table has been expanding for billions of years, while your tape measure politely tries to keep up. The region we can observe is far larger than one might first guess from the age of the universe. It is an immense sphere of accessible history, filled not with things as they are all at one universal now, but with things as their light reached us from different times. Inside this bubble, the universe is not arranged like a tidy collection of objects scattered evenly through space. On smaller scales, it is lumpy and dramatic. Galaxies gather in groups and clusters. Clusters gather along vast filaments. Between those filaments lie immense voids, regions that are not completely empty but are far emptier than the crowded lanes of the cosmic web. If we could step outside ordinary human scale and see galaxies as points of light across hundreds of millions of light years, the universe would look something like a glowing network, a structure of threads and knots. The knots are clusters, the threads are filaments, the open spaces are voids. It is not unlike foam or a sponge, or perhaps a very ambitious spiderweb made by a spider with a deep interest in gravity. This structure grew from tiny variations in the early universe. Slightly denser regions attracted more matter. Gravity amplified small differences. Over billions of years, matter collected into the grand architecture we now map. But when we zoom out far enough, the lumpiness begins to smooth. The universe looks broadly similar in every direction. This is one of the foundations of modern cosmology. On the largest scales we can measure, there does not seem to be a special direction where everything changes completely, nor a central region from which all structure flows. The observable universe appears roughly uniform at enormous scales. This does not mean every place is the same, just as saying a beach is made of sand does not mean every grain is identical. It means that the overall statistical pattern looks similar wherever we look. This matters because it gives us confidence that our observable bubble is not a bizarre special patch, at least not obviously. It may be a fair sample of a much larger universe. That phrase, fair sample, is doing a great deal of work. If our observable universe is only one region within a much larger whole, then we must ask whether the part we see represents the whole accurately. Suppose you were given one spoonful of soup and asked to describe the entire pot. If the soup has been stirred well, your spoonful may tell you quite a lot. If it has not been stirred, and your spoonful happens to contain all the pepper, you might form an overly dramatic opinion. Cosmology faces a similar challenge, though with fewer spoons and more satellite data. We can observe only one cosmic patch. We cannot travel outside it and compare samples. So we study the smoothness of the cosmic microwave background, the distribution of galaxies, the expansion history, and the large-scale geometry of space. These clues suggest that our region is not wildly unusual, but they cannot prove everything about what lies beyond. There is a term for the uncertainty that comes from having only one observable universe to examine. It is sometimes called cosmic variance. It means that because we can observe only one patch of the universe, there are limits to how precisely we can know whether certain features are universal or just local quirks on an enormous scale. It is the cosmological version of listening to one verse of a song and trying to decide whether the whole album uses the same instruments. You may have strong evidence, but you do not have the entire recording. Scientists handle this by combining many observations, building models, and checking whether the patterns we see fit what those models predict. Still, the fact remains, we have one sky, a magnificent sky, a deeply informative sky, but one sky. Within that sky, the cosmic microwave background forms a kind of surrounding screen of earliest visible light. It comes from every direction, not because we're inside a shell that physically surrounds us today, but because wherever we look far enough, we are looking back to the time when the universe became transparent. The light began its journey from matter that has since moved and evolved. What we see as the background glow is not a distant wall sitting in place. It is the oldest layer of our past view. If that sounds hard to visualize, you are in good company. The universe is under no obligation to be easy to picture, which is inconsiderate but apparently allowed. The important thing is that the background glow marks the limit of direct vision with light, and it gives us a map of the early universe in every direction. That map is extraordinarily valuable. Its tiny variations tell us about the density differences that later grew into galaxies. Its overall pattern tells us about the contents and geometry of the universe. From it, scientists have inferred the relative roles of ordinary matter, dark energy, and radiation in shaping cosmic history. It is a little like finding an old receipt from the universe's childhood and realizing it contains the ingredients list for everything that followed. Ordinary matter, the stuff of stars, planets, people and biscuits, is only a small part of the total cosmic budget. Dark matter, which does not shine or absorb light but reveals itself through gravity, makes up much more of the matter. Dark energy, the name given to whatever is driving the accelerated expansion of the universe, dominates the large-scale behaviour today. These components shape the bubble we observe and influence what its future will be. The presence of dark energy is especially important for the boundaries of what we can ever observe. Because cosmic expansion is accelerating, there are galaxies visible to us now whose future light will never reach us. We can see them as they were, but we will not see what they become indefinitely. Over time, their light will become more stretched, more faint, and eventually effectively lost beyond the horizon. This gives the observable universe a strange emotional quality. It is not just a bubble of what we can see now. It is also a temporary archive. Some records are arriving now that future observers may not be able to collect. The universe is still visible in its grand connected structure at this stage of cosmic history, but in the far future that view may fade. The local group of galaxies bound together by gravity will remain. Farther galaxies will slip beyond practical detection as expansion carries them away. This does not happen on human timescales in any noticeable way. You do not need to rush outside tonight to say goodbye to a galaxy before breakfast. But on cosmological timescales, the change is real. The observable bubble evolves. New ancient light can arrive from some regions, but the accelerating expansion places a limit on future communication. This is why cosmologists distinguish between different kinds of horizons. There is the limit of what we can see now. There is the limit of what we could ever see if we waited forever. There is the limit of what we can influence. These horizons are related but not identical. The universe, as usual, provides more than one boundary, when one would have been easier for everyone involved. Thinking of our observable universe as home may sound odd, because most of it is not remotely hospitable. It is full of vacuum, radiation, dark matter, black holes, supernova remnants, galaxy clusters, cold gas, hot plasma, and distances so large that a simple trip to the shops feels delightfully manageable by comparison. Yet it is home in the sense that it is the region whose history is connected to ours. Every atom in your body was forged inside the observable universe. The hydrogen in you traces back to the early universe. The carbon, oxygen, nitrogen, calcium and iron were made in stars and stellar explosions within the long history of cosmic structure. The Sun formed from enriched gas in the Milky Way. Earth formed around it. Life emerged here, eventually producing creatures who use telescopes, mathematics, and occasionally midnight snacks to ask what lies beyond the cosmic horizon. We are not separate from the observable universe. We are one of the ways it has become aware of its own visible patch. That thought can sound grand, but the science behind it is straightforward. The elements needed for rocky planets and living chemistry were not present in large amounts at the beginning. They were produced over generations of stars. Stars form, burn, fuse lighter elements into heavier ones, and return material to space through winds and explosions. Later stars and planets form from that enriched material. This means our existence depends on cosmic time. A universe too young would not yet have made the ingredients for Earth. A universe too old might have a very different sky. With many distant galaxies lost beyond the horizon, we exist in a middle era, after enough stellar history to make complexity, but before expansion has hidden too much of the wider cosmos. It is a rather fortunate time to be curious. The observable bubble also contains the evidence that allows us to understand our origins. Without distant galaxies, we would know much less about cosmic evolution. Without the background glow, we would know much less about the early universe. Without the large-scale distribution of matter, we would have fewer clues about dark matter and the growth of structure. Our bubble is not merely a region, it is a record. It contains nearby objects that show us what the universe is like in its mature state, and distant objects that show us earlier stages. Because light travels at a finite speed, the observable universe preserves its own history across distance. It is a museum where the exhibits are not arranged behind glass but scattered through space, and the older exhibits are farther away. Of course, museums can be incomplete. Some displays are missing, some labels are hard to read, some of the lighting is terrible. The Cosmic Museum is no different. Dust can obscure light. Faint galaxies can lie below detection limits. The earlier stars remain difficult to observe directly. Black holes hide behind event horizons. Dark matter does not announce itself with a cheerful glow. Dark energy is inferred from the behavior of expansion, not seen in a jar. We build understanding by combining many imperfect clues. This is one of the strengths of modern cosmology. It does not rely on a single photograph or one dramatic observation. It uses many independent lines of evidence. The expansion of space, the background radiation, the abundance of light elements, the structure of galaxies, the bending of light by gravity, the motion of clusters, exploding stars used as distance markers, and more. Each clue helps define the bubble we observe and the history it contains. Still, there remains a boundary beyond which the clues become indirect. We cannot observe beyond our horizon directly, and that means our bubble is both a source of knowledge and a limit on knowledge. It is like living inside one enormous room with windows looking backward in time. The windows are astonishing, but they do not show every room in the house. We can study the architecture, infer the building materials, listen for echoes and compare what we see in different directions. We may conclude that the house likely continues beyond our room. We may even develop theories about its overall shape. But we should remember where the evidence comes from. It comes from inside our observable bubble. This is where the idea of the whole universe becomes slippery. In everyday speech, universe means everything. In observational cosmology, however, we often have to distinguish between the observable universe and the universe as a whole. The observable universe is the part we can access through signals. The whole universe may be much larger, perhaps enormously larger, perhaps infinite, or perhaps finite in a shape that has no edge. We do not yet know. Our observable bubble gives us clues, but not a final answer. It is possible that the full universe continues with the same broad properties far beyond what we can see. It is possible that there are regions with different conditions at scales beyond our horizon. Some ideas even suggest many separate cosmic regions produced by early inflation. But before we wander there, it is worth appreciating the remarkable fact that we can say anything at all. After all, we are small observers on a small planet near one star in one galaxy. We cannot travel to distant clusters. We cannot collect a sample from the cosmic microwave background in a bucket, though one suspects someone would try if funding allowed. We cannot step outside the universe to photograph it from a polite distance. And yet we have measured its age, traced its expansion, mapped its ancient light, discovered the cosmic web, inferred invisible matter, and learned that our visible region is not likely the whole. This is not because humans are large. It is because light carries information, and because the laws of physics leave patterns behind. The observable bubble is vast, but it is also readable. One helpful image is to think of our observable universe as a library where every book is already in motion toward us. Some books arrived long ago and sit open nearby, like the moon and sun and neighbouring stars. Some are still arriving from distant shelves, their pages faded and stretched by the journey. The oldest readable volume is the background glow from the early transparent universe. Beyond the library walls there may be more shelves, more rooms, perhaps more books than we could ever count. But the books that have reached us are enough to tell a coherent story, not a complete story, but a deep one, a story of expansion, cooling, structure, stars, galaxies, planets, and the rise of observers who can wonder about the shells beyond the wall. So the observable bubble we call home is not small in any human sense. It is larger than imagination can comfortably hold. Yet compared with what may exist beyond it, it may be only a patch of visibility. It is centered on us, but not because we are central. It has an edge, but not because the universe ends there. It contains the oldest light we can see, but not the beginning of existence itself. It shows a universe that is structured on smaller scales and smooth on the largest scales. It reveals a cosmos shaped by ordinary matter, dark matter, radiation, and dark energy. It holds our entire accessible past, from the background glow to the formation of galaxies to the star that warms this planet. And around it, beyond the reach of current signals, lies the question that drew us here in the first place. If this bubble is only what we can observe, then what continues beyond the cosmic curtain, outside the glow of our lantern, where the same universe may stretch on unseen, or where stranger possibilities may begin to appear? If the observable universe is the bubble of information around us, then the next question is wonderfully natural. What is outside the bubble? Not outside in the sense of stepping beyond a wall, or opening a door at the end of space, or finding a little maintenance corridor where someone has been keeping the laws of physics in boxes. Outside simply means beyond the distance from which light and other signals have reached us. It means beyond the cosmic horizon, and the most sensible answer, at least to begin with, is not the strangest one. It is that there is probably more universe out there, more space, more matter, more dark matter, more galaxies, more long filaments of the cosmic web, more enormous voids, more stars forming and dying, more black holes sitting quietly at the centres of galaxies like very serious librarians who have no intention of returning anything. The observable universe may be vast beyond ordinary imagination, but it may still be only a local portion of a much larger whole. This is not just a guess made because humans enjoy extending patterns. It comes from what we observe inside our own visible region. On very large scales, the universe looks broadly uniform. It has structure, certainly. Galaxies gather into groups and clusters. Clusters connect along wide filaments. Voids open between them like great dark chambers. But when astronomers average across enormous distances, the universe looks much the same in all directions. There is no obvious sign that we are near an edge. There is no side of the sky where galaxies abruptly stop, no direction where space looks young, while the opposite direction looks old in some completely incompatible way. The background glow from the early universe is also astonishingly even, with only tiny variations. Those variations matter deeply, because they later grew into galaxies and clusters, but the overall smoothness suggests that our visible patch is part of something larger and more regular. If the part we can see is a fair sample, then the region beyond our horizon may continue in the same general way. A simple comparison is a foggy landscape. If you are standing in mist and you can see a few fields around you, and those fields look fairly ordinary in every direction, you might reasonably suspect that the countryside continues beyond the mist. You would not know exactly where every stream runs or where every tree stands, but you would not assume that the world ends at the edge of visibility. The same logic applies in cosmology, with the important difference that our fog is not made of water droplets. It is made of distance, time, expansion, and the finite speed of light. Beyond our view, the universe may carry on, not as a duplicate of what we see, but as the same kind of thing. More galaxies arranged differently, more regions with their own histories, more ancient light reaching observers we will never meet. That possibility is already enough to stretch the mind. The observable universe contains an enormous number of galaxies. Each galaxy can contain billions of stars. Many stars likely have planets. Some planets may be bare rock. Some may be gas giants. Some may be icy worlds. Some may have oceans. Some may have weather that would ruin anyone's picnic across an entire hemisphere. And that is just within our observable region. If the universe continues beyond our horizon in roughly the same way, then the amount of unseen cosmic real estate could be staggering. There may be galaxies beyond our view whose light has not reached us and never will. There may be planets beneath skies that contain constellations completely absent from ours. There may be stars that formed from clouds of gas whose history will never enter any telescope on Earth. All of it could be part of the same universe, governed by the same broad laws, yet forever outside our direct knowledge. The first possibility, then, is continuity. Beyond the cosmic curtain lies more of the same grand pattern. This is the cautious answer, the one most closely tied to what we can actually infer. It does not require exotic new physics or other universes. It simply says that the observable universe is not special enough to be the whole. The full universe may extend far beyond what we can see, perhaps by a great amount. In that larger space, our visible region would be like one patch of ocean seen through a porthole. The patch is real. It tells us about waves, colour, motion, and weather. But it is not the entire sea. There is also the possibility that the universe is infinite. This is one of those ideas that sounds simple when said quickly, and becomes increasingly slippery the longer you hold it. An infinite universe would not have an edge anywhere. Space would continue without end. No matter how far you travelled, there would be more distance ahead. This does not mean the universe must have a centre. In fact, an infinite universe has no central point in the usual sense. Every location can see itself as surrounded by more space. If the universe is infinite and broadly similar everywhere on large scales, then beyond our observable bubble there is not merely a little more universe, but endlessly more. More galaxies without a final boundary, more cosmic web without a last thread, more voids without a final emptiness beyond them. Whether the universe is infinite is not something we currently know. Observations show that space, on the largest scales we can measure, appears very close to flat. In cosmology, flat does not mean flat like a sheet of paper floating in a room. It means that the large-scale geometry behaves in a certain way. In a flat universe, parallel paths stay parallel in the ordinary sense, and the rules of geometry match what we expect from everyday space when we ignore local curves caused by gravity. A perfectly flat universe could be infinite, but it does not have to be. The measurements tell us that if there is curvature, it is very small across the region we can observe. That allows for an infinite universe, but it also allows for a universe so large that any curvature is too subtle for us to detect from our limited patch. It is rather like standing on Earth and seeing the ground around you look flat. That does not prove the entire planet is flat. It proves only that your local view is too small to reveal the curvature clearly. Fortunately, in this case, no one needs to argue with a globe on the internet. The point is just that local flatness does not always reveal the full shape. A finite universe can also have no edge. This sounds odd because in daily life, finite things usually have boundaries. A table has edges, a book has covers, a biscuit has a perimeter, though not for long if it is near tea. But geometry offers more interesting possibilities. The surface of Earth is finite in area, yet if you travel along it in one direction you do not reach an edge. You eventually return to where you began. The surface is unbounded. Space itself could, in principle, have a shape that is finite but unbounded in a higher dimensional sense. If that were true, travelling far enough in one direction through space might eventually bring you back around. Not because you turned, but because of the global shape of space. This is difficult to picture, because our brains are built for rooms, roads, and cups of tea. Not for the possible topology of the entire universe, but mathematically such shapes are possible. Astronomers have looked for signs that space wraps around in this way. One possible clue would be repeated patterns in the sky. If light could circle around the universe, we might see the same galaxy or the same region of the cosmic microwave background in more than one direction, appearing at different ages because the light took different paths. It would be a little like living in a hall of mirrors, except the mirrors are space itself, and the reflections are ancient galaxies. So far, no convincing evidence of such a cosmic wraparound has been found. That does not rule out all finite, unbounded models. The universe could be much larger than the observable region, so any repeats would lie beyond our ability to detect. But it does mean that if space has a global shape that loops back on itself, it is not obvious within the patch we can see. Another possibility is that beyond our horizon the universe continues, but with variations so large that our region is not fully representative. The part we observe may look smooth and uniform on large scales, but perhaps on scales far beyond our horizon there are differences. Maybe matter is distributed differently. Maybe the average density changes over immense distances. Maybe there are regions where the history of structure formation unfolded in unusual ways. These ideas are harder to test because the relevant scales are beyond our view. The cosmological principle, the assumption that the universe is broadly the same everywhere on sufficiently large scales, has worked very well inside what we can observe. But whether it holds forever beyond the observable region is a deeper question. Science can say what the evidence supports. It must be more careful about what lies beyond any possible measurement. There is a stronger and more speculative version of this idea. Perhaps beyond our observable universe, conditions are not merely arranged differently, but the basic properties of nature differ in some regions. Maybe the values that shape particles, forces, and cosmic expansion are not the same everywhere in the largest possible reality. This is not the standard cautious assumption for the space just beyond our horizon, but it appears in some models connected to the earliest moments of cosmic history. If the early universe underwent a process that created different regions with different physical conditions, then our observable universe could be one region in a much larger collection. Some regions might allow galaxies and stars. Others might be empty, unstable, short-lived, or structured in ways that would make familiar matter impossible. This begins to move toward the idea of a multiverse, which needs careful handling because it is easy for imagination to race ahead wearing a cape. For now, we can simply say that some theories suggest the larger reality may contain regions far stranger than just more galaxies. But before getting too far into the unusual possibilities, it is worth appreciating how much ordinary continuation already implies. If there is more universe beyond what we can see, then there are regions completely absent from our sky. Their light has not reached us. Their events have left no trace in our detectors. A star may explode beyond our horizon, sending a flash into space, and that flash may never cross into our observable bubble. A black hole may merge with another black hole, shaking space with gravitational waves, and those waves may never arrive here. A planet may orbit a quiet star, have oceans, ice, clouds, storms, perhaps even some chemistry that becomes life, and it would still be permanently outside our story. The reality of a thing does not depend on whether it can send us a signal. This is a humbling correction to the usual human habit of equating the known with the real. That said, science cannot simply fill the unseen with whatever we like. It has to ask what the visible universe permits us to infer. The reason scientists expect more universe beyond our view is not because it feels grand. It is because the visible universe gives no evidence of being a special island with an edge nearby. Its large-scale smoothness, its geometry, and its history all fit models in which our observable region is part of a much larger whole. The simplest extension of those models is that the same kind of universe continues beyond our horizon. It may not continue forever. It may not continue unchanged on every imaginable scale. But more of the same is the most grounded starting point. This is sometimes disappointing to people hoping for a dramatic answer, because more universe sounds almost too plain. But plain answers can be enormous. More universe does not mean boring. It means more of the process that built galaxies, stars, planets, and chemistry. It means more matter shaped by gravity over billions of years. It means more places where the early conditions of the cosmos unfolded into structures we will never see. The fact that the likely answer begins with more of what we already know should not make it small. A forest beyond a hill is still remarkable even if it contains trees rather than dragons. Though, to be fair, one should always check carefully before ruling out dragons, especially in dense fog. There is also a strange consequence if the universe is infinite. and if matter is arranged in all possible ways across endless space. In such a universe, there may be only so many ways to arrange particles within a region like our observable universe, provided the rules of physics remain the same and the amount of matter in each region is finite. If space is truly infinite, some arrangements might repeat somewhere far beyond our horizon. There could be distant regions that resemble ours very closely, perhaps even with galaxies like ours, stars like ours, planets like ours. This idea is sometimes discussed as a consequence of infinity, but it belongs to the far edge of speculation. Even if it were true, such regions would be so far away that they would have no practical connection to us. It is not the kind of thing one can verify by sending a message asking whether they also forgot to buy milk. It is an interesting mathematical implication, not an observable neighbour. The thought does, however, help show how different cosmic scale is from everyday scale. On Earth, if two villages are beyond each other's horizon, someone can walk between them. In the universe, beyond the horizon may mean permanently unreachable. There may be no bridge, no route, no future technology that can carry information across certain cosmic separations, because the limitation is not engineering but the structure of space and time. This does not mean travel and discovery are pointless. It means the universe contains horizons that are not like ordinary distances. The observable bubble is not a frontier waiting for a faster ship. It is a boundary in what can be connected by signals. One might ask whether there is any way to know about what lies beyond without receiving light from it. The answer is perhaps indirectly, but only with great caution. For example, if something beyond our horizon affected the conditions inside our horizon in the early universe, it might have left an imprint. Some scientists have searched for unusual patterns in the cosmic microwave background that could hint at influences from outside our visible region, or even collisions between different cosmic regions in speculative models. So far, there is no widely accepted evidence for such effects. Most of the observed patterns can be explained by standard cosmology. That is not a failure. It tells us that the simplest picture remains strong. The universe we can observe behaves very much like a patch of a larger, smooth, expanding cosmos. The question also depends on what we mean by beyond. There is beyond the current observable universe, meaning regions whose light has not reached us yet. There is beyond the event horizon, meaning regions from which light emitted now will never reach us because expansion prevents it. There is beyond the surface of last scattering, meaning earlier times hidden from ordinary light because the universe was opaque. There is beyond our theoretical confidence, meaning possibilities that exist in equations but not yet in evidence. These different beyonds often get mixed together, especially in casual conversations and late-night documentaries with dramatic music. Keeping them separate helps the question become clearer. The space just beyond our observable horizon may be much like the space we see. The earliest moments before the oldest light require different tools to understand. The possibility of separate universes belongs to a more speculative layer. Still, all these meanings share one thing. They remind us that observation has limits. The universe is not a complete object laid out in front of us. We're inside it, receiving information along paths allowed by light, gravity, particles, and time. Our knowledge is shaped by where we are and when we exist. That does not make the knowledge weak. It makes it situated. We know a great deal about our observable bubble because the universe is consistent enough to be studied. We can use the laws of physics tested nearby to interpret light from far away. We can compare different signals and build a coherent history. But beyond the cosmic curtain, we move from direct observation into inference, and from inference toward speculation. Each step must be labelled honestly, like jars in a kitchen where one contains flour, one contains sugar, and one contains something mysterious that may have been useful in 2017. What might lie beyond, then, is a layered answer. Most immediately, probably more galaxies, more cosmic web, more expanding space, more of the universe continuing beyond our visible limit. On larger or stranger scales, perhaps a finite but unbounded cosmic shape, or an infinite expanse without edge, or regions so distant that their conditions differ from ours in ways we cannot yet test. In more speculative theories, perhaps other domains born from early cosmic inflation, separated from us not by ordinary distance, but by the structure of the larger cosmos. None of these possibilities should be treated the same. Some are supported by the observed smoothness and geometry of our universe. Some are mathematically possible. Some are motivated by theories that may or may not describe reality. The careful answer is not a single dramatic picture, but a range of possibilities arranged from conservative to adventurous. There is something peaceful about beginning with the conservative possibility. Beyond the curtain, the universe may simply go on. It does not need to become stranger the moment it slips beyond our sight. The hidden field may continue beyond the lantern glow. The sea may continue beyond the horizon. The sky may contain light that will never reach us, not because anything magical blocks it, but because the universe is large, old, and expanding, and that is already enough. We do not have to imagine an edge where reality stops. We can imagine continuation, and with it a universe whose full size may exceed not only our instruments, but our ability to form a mental picture. And yet, the reason this question continues to pull at cosmologists is that the early universe may have done something extraordinary. The smoothness of our observable bubble, the apparent flatness of space, and the absence of certain expected relics all suggest that in its first moments, the universe may have expanded at an astonishing rate. This idea, known as cosmic inflation, gives a possible explanation for why regions now far apart look so similar, and it also opens the door to a universe far larger than the one we observe. To understand what might lie beyond the curtain, we have to turn back to that earliest burst of expansion, when space may have grown so quickly that it stretched a tiny region into something vast enough to contain everything we see and far more besides. To understand what might lie beyond the cosmic curtain, we have to go back to a time when the universe was so young that the word young hardly seemed strong enough. Not young like a child or a sapling, or a fresh cup of tea still too hot to drink, but young in the deepest possible sense. The universe had barely begun. Space was hot, dense, and filled with energy. The familiar things we use to organize reality had not yet settled into their later forms. There were no stars, no galaxies, no planets, no quiet kitchens, no one wondering why the kettle sounds louder at night. And yet, in that incredibly early moment, something may have happened that shaped everything we can see today, and possibly much more that we will never see. Space may have expanded with astonishing speed. Not matter flying through space, but space itself stretching, swelling, growing so quickly that a tiny region became enormous. This idea is called cosmic inflation, and it is one of the most important attempts to explain why the universe looks the way it does. Inflation was proposed because the universe, when viewed on the larger scales, has some features that are surprisingly difficult to explain without it. The first of these is the remarkable smoothness of the cosmos. When we look at the ancient background glow, the oldest light that can reach us directly, it is nearly the same in every direction. One side of the sky has almost the same temperature as the other. Regions separated by enormous distances look as though they somehow agreed on their conditions long ago. This is strange because, without some special explanation, those regions should never have had time to communicate with each other. Light could not have crossed from one side to the other in the time available. It is rather like finding 2 cups of tea on opposite sides of a very large house, both at exactly the same comfortable temperature, even though no one had time to carry heat between them. You would suspect there was a shared history. Perhaps they were once close together before being carried apart. Inflation provides that shared history. According to the inflationary idea, the regions of space we now see in opposite directions were once much closer together, close enough for conditions to even out. Then, during a brief burst of extremely rapid expansion, they were stretched far apart. So when we observe the sky today and find that distant regions look similar, inflation says they look similar because they once belonged to a small connected patch. They were not strangers trying to coordinate across impossible distance. They were neighbours before space grew between them. This is a simple idea at heart, even though the physics behind it is not simple at all. It turns a puzzle about distant regions into a story about a once tiny region becoming vast. Another puzzle inflation helps with is the apparent flatness of space. On the largest scales we can measure, the geometry of the universe appears very close to flat. Again, flat here does not mean flat like a tabletop. It means the rules of large-scale geometry behave in the ordinary way without strong overall curvature. This is surprising because the early universe could have had many possible curvatures. If the curvature had been even a little different early on, it might have grown more obvious over time. Instead, the universe looks balanced in a very particular way. Inflation offers an explanation by stretching space so enormously that any initial curvature would be smoothed out. Imagine the surface of a balloon. Up close, when the balloon is small, the curve is easy to notice. But if you could expand that balloon to an enormous size while standing on a tiny patch of its surface, your local patch would look almost flat. The curve would still exist on the largest possible scale, perhaps, but it would be too broad for your small view to detect. Inflation does something like this to the universe. It stretches any initial wrinkles until the region we can observe looks smooth and nearly flat. There is also a puzzle involving certain hypothetical relics from the early universe. Some theories suggested that the hot young cosmos should have produced heavy exotic leftovers, objects or particles that we do not seem to find today. Inflation can help by diluting them. If such relics existed before inflation, the rapid expansion would spread them out so widely that our observable universe might contain none at all, or far too few for us to detect. This is the cosmic equivalent of dropping one raisin into bread dough and then expanding the loaf to the size of a continent. Somewhere perhaps the raisin still exists, but good luck finding it in your slice. Inflation takes whatever was present before and stretches it across such a vast volume that many unwanted leftovers become effectively invisible. These explanations make inflation attractive, but inflation is not just a convenient patch placed over awkward questions. It also makes a powerful prediction. Tiny quantum fluctuations in the very early universe would have been stretched by inflation to enormous scales. These small variations would become the seeds of later structure. After inflation ended, some regions were slightly denser than others. Gravity then took over. The denser regions attracted more matter. Over vast periods of time, those small differences grew into galaxies, clusters, filaments, and the cosmic web. In this view, the largest structures in the universe began as tiny fluctuations in the earliest moments, stretched across space by inflation and then amplified by gravity. That is a remarkable thought. The great galaxy clusters, the long glowing threads of cosmic structure, the very pattern of matter across the sky, may trace back to microscopic irregularities from before the universe had atoms, stars, or even light travelling freely. This gives inflation a strong connection to observation. The pattern of tiny temperature variations in the cosmic microwave background is not random noise. It has a structure that can be measured. Cosmologists compare that structure to predictions from models of the early universe. Inflation fits many of these observations very well. It explains why the universe is so smooth overall while still having tiny variations. It explains why those variations have the kinds of patterns we see. This does not mean every detail of inflation is settled. The broad idea is influential because it solves several problems at once and matches important evidence, but the exact mechanism remains uncertain. Scientists do not yet know what drove inflation. They often describe it in terms of a field, a kind of energy filling space that caused rapid expansion, but the precise identity of that field is unknown. It is one thing to say the universe seems to have undergone inflation. It is another to say exactly what physical process made it happen. This is where the story becomes both fascinating and carefully uncertain. Inflation is widely discussed because it works well as an explanation, but it is not a finished photograph of the earliest universe. It is more like a strong outline, with certain details still waiting to be filled in. Different versions of inflation make different predictions. Some are already disfavored by observations, others remain possible. Scientists look for clues in the cosmic microwave background, in the distribution of galaxies, and in possible signals from gravitational waves produced in the earliest moments. Detecting such signals would help narrow the possibilities, but they are extremely difficult to find. The universe does not simply hand over its earliest diary. It leaves faint marks on old light and expects us to build satellites, detectors, and very patient statistical methods. The phrase rapid expansion can also be misleading if we imagine an explosion. Inflation was not a blast of matter into empty space. There was no outside room into which the universe expanded. Space itself expanded. Distances within space grew. This is always the difficult part because our everyday minds want expansion to happen into something. A loaf expands into the oven. A balloon expands into the surrounding air. A cat expands into the exact amount of available sofa, with great confidence. But the universe is not known to be expanding into a larger external space. In cosmology, expansion means the distances between far apart points in space increase. During inflation, that increase may have been unbelievably fast. Not objects racing through space faster than light, but space itself stretching so quickly that regions once close together became separated beyond each other's horizons. This matters for the question of what lies beyond the observable universe. If inflation occurred, it likely made the full universe much larger than the part we can see. Our observable bubble may be only a tiny region within the space created or stretched during inflation. The same process that explains the smoothness of our sky also suggests that the universe beyond our horizon could extend tremendously far. Imagine starting with a small patch of fabric and stretching it so much that the portion visible through your window looks almost perfectly smooth. You could examine your patch and learn a great deal, but the fabric beyond the window might continue for an enormous distance. Inflation takes a small connected region and stretches it until our observable universe fits inside it with room to spare. How much room depends on the details, and those details are not fully known. It could be vastly more space than we see. It could be so much more that the observable universe is a tiny speck by comparison. This is one of the reasons inflation changes the emotional scale of cosmology. Before thinking about inflation, the observable universe already seems almost impossible to comprehend. It contains everything whose light has reached us across cosmic time. But inflation suggests that the entire region we observe may be just one small visible patch of a much larger expanded domain. The universe did not merely grow. It may have grown too fast for our view ever to catch up. It may have stretched regions apart so thoroughly that they became permanently hidden from one another. If so, beyond our horizon is not just more space by a modest amount. It may be an unimaginably larger continuation of the same inflated region, with galaxies, voids, and structures that share an origin with ours but are forever out of contact. The idea also helps explain why the universe appears so uniform. If our whole observable bubble came from a small pre-inflationary region, then it makes sense that it has broadly similar conditions everywhere. It is like taking a tiny piece of dough that has been well mixed and stretching it into a huge sheet. Every part of the sheet comes from the same original mixture. Of course, the universe is not dough, though dough has done admirable service as a cosmological teaching tool over the years. The point is that inflation gives our visible region a common origin. The smoothness of the cosmic microwave background is no longer mysterious in the same way. It is a memory of closeness before expansion. But inflation does not erase all differences. In fact, it preserves and enlarges tiny differences. Those quantum fluctuations stretched during inflation became the seeds of structure. This is a beautiful balance. Inflation makes the universe smooth overall, but not perfectly smooth. If it had made everything exactly uniform, there would be no galaxies, no stars, no planets, and no one lying in bed listening to a quiet voice explain why there are no galaxies. The tiny imperfections mattered. Gravity needed something to work with. Slightly denser regions became the beginnings of cosmic architecture. So inflation gives us both the large-scale sameness and the small-scale variation. It smooths the canvas but leaves the faint marks from which the picture later grows. This is one of the more remarkable things about the early universe. The grand structures we observe today may have their roots in quantum uncertainty. Normally, quantum effects seem confined to very small scales, the realm of particles and atoms. But inflation stretched those tiny fluctuations across cosmic distances. The extremely small became astronomically large. This means the pattern of galaxies across the sky may carry an imprint of the quantum behavior of the earliest universe. It is as if the universe took the faintest tremble in its first moment and enlarged it until it became the scaffolding for billions of galaxies. That is not poetry. That is close to the actual logic of the theory, though said with fewer technical terms and a much softer cushion. At some point, inflation had to end in our region. The rapid expansion slowed, and the energy driving inflation transformed into the hot particles and radiation that filled the early universe. This transition is often described as reheating. The universe became hot and dense in the way associated with the early Big Bang picture. In this sense, inflation does not replace the Big Bang model. It adds a stage before the hot, expanding universe described by the standard cosmological story. The Big Bang in modern usage often refers not to a single explosive instant in space, but to the hot, dense early state from which the universe expanded and cooled. Inflation is a proposed earlier process that set up that hot state. It helps explain why the hot universe began with the conditions it had. This is important because people often imagine the Big Bang as the universe exploding from a single point into darkness. That picture is not quite right. The Big Bang was not an explosion in space. It was the expansion of space everywhere. Inflation makes this even clearer. During inflation, every region of space expanded. There was no central blast. Every observer, if observers had existed, which they very much did not, would have seen other regions moving away as space stretched. The universe did not need a center. The expansion happened throughout space. This is why asking where the Big Bang happened is a bit like asking where on the surface of Earth the surface happened. It happened everywhere in the observable universe, and likely far beyond. If inflation stretched space so dramatically, it also affects how we think about the horizon. Regions now beyond our view may once have been close to the region that became our observable universe. They may share the same early conditions, but inflation carried them so far away that their light has not reached us, and perhaps never will. The cosmic curtain, in this view, is partly a consequence of that early stretching. It is not just that the universe is old and light is finite, it is that the universe may have expanded so much that the full connected domain is far larger than the accessible part. Inflation takes the limits we discussed earlier and places them inside an even bigger story. There is a further twist. In many models, inflation does not necessarily end everywhere at once. It may end in some regions while continuing in others. Where it ends, a hot universe like ours can form, with particles, radiation, and eventually galaxies. Where it continues, space keeps expanding rapidly. This process can create separate regions, sometimes called bubble universes in popular explanations, though the phrase can be misleading if taken too literally. Each region where inflation ends may become a universe like ours, in the sense of having its own hot beginning and later cosmic evolution. Meanwhile, the space between such regions may continue inflating, carrying them apart so quickly that they can never meet. This idea is known as eternal inflation, and it leads naturally into multiverse scenarios. Now, this is where we need to slow down and keep our slippers firmly on the floor. Eternal inflation is a serious idea in theoretical cosmology, but it is also difficult to test. It may arise naturally from certain versions of inflation, but whether those versions describe our universe is still not known. The possibility of many inflated regions is exciting, but excitement is not evidence. Scientists look for ways such a scenario might leave observable traces, perhaps through patterns in the cosmic microwave background or other relics. So far, there is no confirmed sign that our observable universe collided with another bubble region or carries a clear imprint of one. The multiverse remains a possibility in some theoretical frameworks, not an established observation. It is useful, fascinating, and controversial, which is a combination physics seems to produce whenever the universe is feeling particularly ambitious. Even without eternal inflation, ordinary inflation already suggests that what lies beyond our horizon is far larger than the part we can see. That alone is enough for our question. The observable bubble may be a small portion of a region stretched from a common origin. Beyond it, space may continue with similar properties for distances we cannot measure. The galaxies there, if galaxies formed there, would not be separated from us by a wall. They would be separated by the history of expansion and by horizons. They would belong to the same grand process, but their light would not be part of our sky. One of the gentle lessons of inflation is that size can be deceptive. The observable universe feels complete because it contains everything we can directly study. But if inflation is right, the visible cosmos may be like a small, smooth patch on an enormous sheet. Our observations can tell a great deal about that patch and about the process that stretched it, but they may not reveal the full extent of the sheet. We can infer that it continues. We can model how it may have formed. We can test predictions within our horizon, but we cannot simply look out and see the whole. The universe may have grown too fast, too early, for any observer inside it to see its full reach. And yet, this limitation is also what makes the evidence we do have so valuable. The tiny variations in the background glow, the large-scale arrangement of galaxies, the near flatness of space, and the uniformity of the cosmos are all clues left by that early expansion. They are not loud clues. They are not dramatic in the everyday sense. They are subtle patterns spread across the sky, requiring careful measurement and interpretation. But they point toward a time when the universe changed scale in a way no human experience can match. A small region became cosmic. Tiny fluctuations became the seeds of galaxies. Space stretched so quickly that our present horizon may enclose only a fraction of what was made. So when we ask what is beyond the observable universe, inflation gives a calm but enormous answer. Beyond may be more of the inflated space that shares our origin, continuing far past the reach of light. It may be so large that our observable universe is only a small local neighborhood, and if some versions of inflation are correct, there may be other regions where inflation ended differently, producing cosmic domains with their own histories. This is not yet something we can claim as fact. It is a possibility opened by the physics of the early universe, a possibility that asks us to imagine not an edge, but a vastness produced by expansion itself. From here, the path naturally leads toward the more speculative side of the question. If inflation can create a universe much larger than what we observe, and if in some models it can produce many separated regions, then we are brought to the idea that our cosmic home may not be the only domain of its kind. Not parallel worlds in the casual sense, not a convenient place where every lost sock has made a better life, but a deeper possibility that the larger reality contains many bubble-like regions, perhaps with different histories, perhaps with different conditions, all hidden beyond horizons we cannot cross. Once inflation opens the door to a universe much larger than the part we can see, another question quietly steps in behind it, wearing rather large shoes and looking as though it may stay for tea. If our observable universe is only one region inside a far greater cosmic expanse, could there be other regions so distant, so separated, or so differently formed that calling them part of our universe begins to feel incomplete? Could there be other universes, not in the simple science fiction sense of a mirror Earth, where you remember to water the basil, but in the deeper cosmological sense of separate domains of space and history hidden forever beyond our horizon. This is the multiverse question, and it is one of the most fascinating, controversial, and easily misunderstood ideas in modern cosmology. It sits in that curious region where mathematics, physics, observation, and imagination all gather around the same table, each politely insisting that it brought the most important biscuits. The first thing to say is that the multiverse is not one single idea. It is more like a family of ideas that share a general theme. The theme is that what we call the universe may not be the whole of physical reality. There may be other regions, other domains, other cosmic histories, perhaps produced by the same deep processes that produced our own. Some versions are closely tied to inflation. Some arise from quantum mechanics. Some come from theories about extra dimensions or the landscape of possible physical laws. Some are more speculative than others. Some are carefully motivated by real problems in physics, while others are more like thought experiments that help us ask what our assumptions really mean. So when someone says the multiverse, it is worth asking which one, because otherwise the conversation can become a bit like asking what is in the cupboard and being told objects. Accurate perhaps, but not very helpful when you are looking for the tea bags. The version most closely connected to what we've been discussing comes from inflation. In many inflationary models, the rapid expansion of space does not end everywhere at once. In some regions, inflation stops, the energy driving it changes into particles and radiation, and a hot expanding universe begins. That could be what happened in our region. But elsewhere, inflation may continue. Space keeps stretching at an enormous rate. Then, in another region, inflation stops again, creating another expanding domain. This process can repeat, perhaps endlessly, producing many separated regions where hot universes form inside a still inflating background. These regions are often called bubble universes, though one must be cautious with that image. They're not soap bubbles floating through a bathroom, wobbling gently until someone bumps the tap. They are regions of space where inflation has ended and ordinary cosmic evolution has begun, surrounded by regions where inflation may still continue. The bubble image is useful because it suggests separation. If two such regions form far apart in an inflating background, the space between them can expand so rapidly that they never meet. No light from one reaches the other. No spacecraft could cross the gap. No message could be sent, not even a very determined postcard with excellent stamps. Each bubble region would have its own observable universe inside it, its own history of expansion, cooling, structure formation, and perhaps galaxies and stars depending on its physical conditions. From inside one bubble, observers would see their own cosmic horizon and might infer, as we do, that there is more beyond what they can observe. They would not see the other bubbles directly. Those other regions would be beyond any ordinary form of contact. This is why the multiverse, in the inflationary sense, is not simply a claim that there are more galaxies beyond our horizon. More galaxies beyond our horizon would still be part of our same large cosmic region, sharing broadly the same physical laws and early conditions. Bubble universes are a stronger idea. They may be separated from our region by inflating space in such a way that they are not just far away, but causally disconnected in a more permanent and profound sense. They may also have different properties depending on the underlying physics. In some models, the way inflation ends can vary from bubble to bubble. That means different bubbles might have different amounts of matter, different patterns of expansion, or even different effective laws of physics. This is where the idea becomes both exciting and difficult, because once different physical conditions are allowed, the imagination immediately begins rearranging reality like furniture before checking whether any of it fits through the door. Could another bubble universe have stars? Maybe. Could it have galaxies? Perhaps. Could it have atoms like ours, chemistry like ours, planets like ours? That depends on whether its physical conditions allow such things. the laws and constants we observe in our universe appear finely suited to the formation of complex structures. Gravity is strong enough to gather matter into stars and galaxies, but not so strong that everything collapses immediately. The electromagnetic force allows atoms and chemistry. The particles we know have masses and interactions that permit stable matter. The expansion history of the universe allows matter to clump into galaxies before dark energy dominates too strongly. If some of these properties were different, the universe might be very different. It might expand too quickly for galaxies to form. It might collapse too soon. It might have no stable atoms. It might have only diffuse particles, or black holes, or radiation, or something stranger that does not fit our familiar categories at all. This leads to the Anthropic line of thinking, which is often discussed alongside the multiverse. The basic idea is simple enough, though it can easily be made to sound more mysterious than it needs to be. We observe a universe compatible with our existence, because only such a universe can contain observers like us. If many universes exist with different properties, then it is not surprising that we find ourselves in one where stars, planets, chemistry and life are possible. We could not find ourselves in a universe that never forms atoms or galaxies, because there would be no us there to do the finding. This is not a complete explanation by itself, and it does not replace the search for deeper physical laws, but it may help address why certain features of our universe seem unusually suitable for complexity. If there is a vast collection of cosmic domains with different properties, then our presence selects one of the rare domains where our kind of observation can happen. Some scientists find this reasoning useful, others are cautious or dissatisfied with it, because it can feel less like explaining a feature and more like saying, well, here we are. Physics usually tries to derive why something must be the way it is, not merely why we should not be surprised to see it from our particular vantage point. The Anthropic argument can be helpful when combined with a theory that actually predicts a range of possible universes. Without that, it risks becoming too flexible. If an idea can explain almost anything after the fact, it becomes harder to test. Science likes ideas that take risks, ideas that could have been wrong if the universe had turned out differently. The multiverse often struggles here, because the other universes, if they exist, may be forever beyond direct observation. That does not automatically make the idea unscientific, but it does mean we have to be very clear about what is being tested. One possible way to test some multiverse scenarios would be to look for traces left by interactions between bubble universes. If our bubble collided with another bubble in the early past, perhaps that event could leave a pattern in the cosmic microwave background, such as a faint circular mark or an unusual asymmetry. Scientists have searched for such signs. So far, there is no confirmed evidence. The background glow is remarkably well explained by the standard picture of inflation and cosmic evolution, with its tiny variations acting as the seeds of structure. That does not rule out every bubble universe model, because many collisions may never happen, or may leave no detectable trace, or may have occurred outside our observable region. But it does mean we do not currently have a clear observational fingerprint of another bubble touching ours. The cosmic curtain remains closed, and it is not polite enough to rustle dramatically just when the cameras are ready. There is also another kind of multiverse that comes from quantum mechanics, especially the many worlds interpretation. This idea is different from bubble universes in cosmology. It does not say there are distant regions of space beyond our horizon. Instead, it suggests that every quantum event with multiple possible outcomes corresponds to branching histories of reality. In one branch, a quantum measurement has one result. In another branch, it has a different result. The universe, in this view, does not choose just one possibility. All possibilities occur, each in its own branch. This is the version that most resembles popular ideas of alternate realities, though the actual physics is more subtle and less likely to involve convenient plot devices. It is not about stepping through a glowing doorway and meeting a version of yourself who became a professional violinist. It is an interpretation of what quantum equations mean when they describe probabilities. The many worlds idea is fascinating, but it belongs to a different category from the cosmological multiverse. Bubble universes would be separated in space and cosmic history. Quantum branches would be separated in the structure of the wave function, not by travelling far enough with a powerful telescope. Both ideas expand the meaning of reality beyond what we directly experience, but they do so in very different ways. Mixing them together can create confusion. It is a bit like mixing maps of the London Underground with maps of ocean currents. Both are maps, both involve movement, and both can get you lost, but not in the same manner. Another route to multiverse thinking comes from theories that attempt to describe all forces and particles within a deeper framework. Some versions suggest that there may be a vast landscape of possible vacuum states, each with different physical properties. In ordinary language, this means that the underlying theory might allow many different ways for a universe to settle into stable conditions. Each settlement could produce different particles, forces, or constants. If cosmic inflation populates many of these possibilities by creating many bubble regions, then different universes could realize different parts of this landscape. This is one of the ways inflation and high-energy theory become linked. The larger reality might not just produce many regions, it might produce regions with different rules. This is a powerful idea, but again, it is not established fact. The mathematics behind these theories is complex and the connection to observation is difficult. We do not currently have a confirmed theory that tells us exactly which universes exist, or how likely each kind would be. This creates what scientists call a measure problem, though for our purposes we can describe it more gently. If there are infinitely many bubble universes, how do you compare how common one type is with another? In ordinary life, if you have a jar of biscuits, you can count how many are chocolate and how many are plain, assuming no one eats them during the experiment. But if the jar is infinite, and new biscuits are appearing all the time in different cupboards, counting becomes rather less straightforward. In eternal inflation, probabilities can be tricky, because the process may produce endless amounts of space and endless numbers of regions. Without a clear way to define what typical means, predictions become difficult. This is one reason the multiverse remains controversial. It may arise naturally from some serious theoretical ideas, but it is hard to test, hard to define statistically, and easy to misuse as an explanation for things we do not yet understand. Good scientists are not against strange ideas. Physics has accepted many strange ideas when evidence demanded them. Relativity is strange. Quantum mechanics is strange. Black holes are strange. The expanding universe itself was once strange, but strangeness alone is not enough. The question is whether an idea connects to observation, makes predictions, explains known facts better than alternatives, and remains disciplined enough not to become a story that can be adjusted to fit any outcome. That is the careful side. The wonder side is still allowed to breathe. If bubble universes exist, then the reality beyond our observable horizon is not merely larger than we can see, it is larger in kind. Our universe would be one domain among many, perhaps one pocket where inflation ended in a particular way, where matter formed, where galaxies grew, where stars forged elements, where at least one small planet developed creatures who look up and ask whether there are other pockets. The scale would be so vast that even the observable universe would be only one room in a mansion, whose other rooms may never share a hallway with ours. And yet, the idea does not require that our universe be insignificant. A room is not meaningless because there are other rooms. A candle is not less real because there are other candles beyond the window. Our cosmic history would still be ours, still rich, still governed by the conditions that made stars and planets and life possible. It is also worth saying that other universes, if they exist, would not necessarily be friendly to imagination. Popular culture often fills alternate universes with recognizable variations of our world. Different choices, different histories, perhaps everyone wearing slightly more dramatic coats. Cosmological bubble universes could be far less familiar. Many might be sterile, some might have no complex matter, some might expand too quickly for structures to form, some might be dominated by physics that has no place for chemistry or stars. Others might be beautiful in ways we cannot describe because their basic ingredients are not ours. The phrase other universe sounds like an invitation to picture another night sky. But in many cases there might be no night sky at all, no observers, no atoms like ours, no stable ground on which anything could stand and wonder. The multiverse, if real, may be mostly not like us. That makes our universe feel both ordinary and special in different senses. It may be ordinary if it is one of many domains produced by a broader process, but it is special to us because it permits our existence. It has the right kind of order and complexity. It has stars that live long enough to enrich galaxies. It has stable matter. It has a cosmic history that allows planets. It has at least one world where living beings can make models of inflation and then explain them in a sleepy voice while someone else slowly relaxes under a blanket. That may not make our universe unique in all reality, but it makes it meaningful from within. Meaning does not require being the only one. It requires being real, connected, and part of a story that can be lived. There is another subtle point. If the multiverse exists, it may be forever hidden, not because our instruments are weak, but because the separation is built into the structure of space and time. We often assume that future technology will eventually reveal everything. This is a hopeful idea, and sometimes it is true. Better telescopes reveal fainter galaxies. Better detectors reveal gravitational waves. Better instruments open new windows. But some horizons are not engineering problems. They are physical limits. A bubble universe separated from ours by eternal inflation may never be observable from here. No improvement in mirror size, computer processing, or cable management will change that. This is uncomfortable for a species that likes solving problems by building larger machines, but it is part of the honesty of cosmology. Some questions may be approachable only through indirect evidence and theoretical consistency, not direct inspection. Still, indirect evidence can be powerful. We have never touched the core of the sun, but we understand it through light, particles, and physics. We have never seen dark matter directly, but we infer it from gravity. We cannot see the early opaque universe with ordinary light, but we learn about it from the background glow and cosmic structure. So the fact that other universes may be unobservable directly does not end the discussion. It shifts the burden. A multiverse idea becomes stronger if it emerges from a theory that also explains things we can observe, and if that theory makes successful predictions inside our observable universe. In that case, the unobservable parts may be consequences of a well-supported framework. They would be like distant regions predicted by a map whose nearby roads have all been checked. You still cannot visit them, but the map has earned some trust. This is why inflation matters so much to the multiverse question. If inflation is strongly supported by observations inside our universe, and if the best versions of inflation naturally lead to eternal inflation, then the multiverse becomes harder to dismiss. Not proven, but tied to a theory with observational roots. On the other hand, if future evidence points to a different early universe model without eternal inflation, the case changes. Cosmology is still active, still testing, still refining. The multiverse is not a final answer resting comfortably in an armchair. It is a possibility standing near the edge of current knowledge, waiting to see whether the evidence invites it further in or asks it to wipe its shoes at the door. There is a quiet discipline in admitting this. The multiverse is not something we know, in the same way we know that galaxies exist. It is not something we have photographed. It is not something we can point to in the night sky. It is an idea suggested by certain theories, especially some versions of inflation and high-energy physics, and it may help explain why our universe has the properties it does. But it remains uncertain. The correct scientific posture is neither to accept it as obvious nor reject it because it sounds strange. The correct posture is to ask what it explains, what it predicts, how it connects to evidence, and whether there are alternatives that do the job better. That may sound less dramatic than announcing the existence of infinite worlds, but it is how science keeps its feet on the ground even while its head is somewhere beyond the cosmic horizon, and perhaps that is what makes the multiverse question so compelling. It is not only about other universes, it is about the limits of explanation. If something lies forever beyond observation, can it still be part of science? If a theory predicts unseen domains as a consequence of explaining visible facts, how seriously should we take those domains? How do we balance humility with curiosity? These are not just technical questions. They shape the way we think about knowledge itself. The observable universe gives us evidence. Theories reach beyond it. Somewhere between the two, science must decide how far it can responsibly lean. As we drift with this idea, it helps not to rush toward the most extravagant image. We do not need to imagine endless copies of ourselves, or cosmic bubbles bumping like soap foam in a sink, or alternate timelines where breakfast makes better decisions. The real question is quieter and deeper. Our visible universe may be one region formed by early cosmic processes. Those processes may have produced much more space than we can see. In some versions, they may have produced other regions with their own histories. Whether those regions exist remains uncertain, but the possibility grows from serious attempts to understand the beginning of our own cosmic domain. It is not fantasy simply because it is vast. It is not fact simply because it is mathematically tempting. So we return to the horizon with a slightly wider imagination and a slightly firmer caution. Beyond the observable universe may lie more of our own cosmic region, continuing with galaxies and voids far past our sight. Beyond that, if inflation unfolded in certain ways, there may be other bubble worlds, other domains where space cooled into different histories, perhaps with different properties, perhaps forever unreachable. The multiverse question does not give us a simple picture to hang on the wall. It gives us a set of possibilities and asks how much reality might extend beyond evidence, and how evidence might still hint at what cannot be seen directly. That leads us to the next and perhaps most important issue of all, not what we can imagine beyond the cosmic horizon, but whether we can ever truly know anything about it, and where the boundary lies between scientific inference, careful uncertainty, and the vast darkness just outside the reach of our light. After wandering through more universe, inflation, and the possibility of other cosmic domains, we arrive at the question that quietly waits behind all of them. Can we ever know what is beyond the observable universe? Not guess, not imagine, not draw a dramatic picture with a black velvet background and a suspicious amount of purple, but know. Can evidence from inside our little bubble of light ever tell us what lies outside it? This is where cosmology becomes both powerful and humble. Powerful, because the universe has left clues everywhere. Humble, because some places may be forever beyond direct contact. The boundary of the observable universe is not just a challenge to our telescopes. It is a boundary in the flow of information. It marks the limit of what has had time to reach us, and in some cases, whatever can reach us. So the answer is not a simple yes or no. It is a careful answer, the sort that arrives with a notebook, a warm drink, and a deep reluctance to exaggerate. The first thing to remember is that science does not require us to see something directly in order to know it is real. This is important because otherwise much of physics would have to pack up early and go home. We do not see the center of the sun directly, yet we understand the nuclear processes that power it through light, particles, and the behavior of stars. We do not see dark matter shining in telescopes, yet we infer its presence from gravity, from the motion of galaxies, from the bending of light, and from the growth of cosmic structure. We do not see the early universe before it became transparent with ordinary light, yet we study it through the afterglow it left behind and through patterns that were written into matter long before the first stars. Science often works by inference. It builds bridges from what is observed to what must have been there to produce the observation. The bridge must be strong, but it does not need to be short. This means that the unseen is not automatically unknowable. The region beyond the observable universe may be hidden from direct view, but the visible universe can still tell us something about it. Our observable bubble has properties. It has a large-scale geometry. It has a pattern of matter. It has an expansion history. It has a background glow that is astonishingly smooth, with tiny variations that match the seeds of later galaxies. These features are not random decorations. They are clues. If a theory explains the clues inside our observable universe and also predicts what lies beyond, then the beyond becomes part of a broader scientific picture. We may not observe it directly, but we may have reasons to believe certain things about it. This is not the same as certainty, but it is not blind guessing either. Think again of standing in a foggy field. You cannot see the land beyond the mist, but the ground under your feet slopes gently downward. You hear a stream somewhere ahead. The trees you can see all grow in the same kind of soil. A path continues into the grey. You do not know exactly what is hidden, but you can make sensible inferences. The path probably does not end abruptly 2 steps beyond visibility. The stream probably continues. The same soil may extend for a while. You would be unwise to claim there is definitely a castle, a dragon, or a small cafe selling excellent scones, but you would also be unwise to say nothing can be known at all. The observable universe is our visible field. The mist is the cosmic horizon. The patterns inside the mist tell us something about the land beyond. The strongest inference is the simplest one. Because the universe looks broadly uniform on very large scales, it is reasonable to think that beyond our horizon there is more universe much like the part we see. This is not proven in the way we prove a nearby object exists by taking a photograph of it. It is a conclusion supported by the large-scale smoothness of the cosmos. The cosmic microwave background looks nearly the same in every direction. The distribution of galaxies, once averaged across enormous distances, does not point to an obvious edge or centre. The geometry of space appears very close to flat across the observable region. These clues suggest that our visible bubble is not a strange isolated island, but part of a larger cosmic expanse. If the same patterns continue beyond our horizon, then the unseen regions may contain more galaxies, clusters, filaments, voids, and dark matter, arranged differently but governed by the same general rules. Could this inference be wrong? Yes, in principle. The universe beyond our horizon could change in some unexpected way. Our observable bubble might be part of a much larger structure, with variations on scales too vast for us to detect. There might be regions where the density is different, or where the geometry curves in a way too subtle to show up inside our patch. Science cannot rule out every possibility beyond observation, simply by saying it seems unlikely. But good science asks which possibilities are supported by evidence, which are allowed but untested, and which are simply inventions floating about with no anchor. More of the same is the cautious expectation because it extends what we already observe. Stranger possibilities require stronger reasons. This is where observations of the cosmic microwave background become especially important. That ancient glow is not just a pretty relic, though it is quite lovely in a grainy scientific way. It is a map of early conditions across the entire visible sky. Its tiny variations tell us how matter was distributed when the universe was young. Its smoothness tells us that distant regions once had very similar conditions. Its pattern helps us measure the contents of the universe and test ideas about inflation. If there were large-scale irregularities, unusual curvature, or evidence of something disturbing our early cosmic neighbourhood, the background glow might reveal traces. Scientists have searched it carefully for such signs. The fact that the standard cosmological model explains it so well is a major reason we trust the broad picture. It does not tell us everything beyond the horizon, but it tells us that our visible region behaves like a consistent part of a larger smooth universe. There have been searches for more exotic clues as well. Some scientists have wondered whether a collision with another bubble universe, if such things exist, might leave a mark in the cosmic microwave background. Perhaps a circular pattern, a strange temperature feature, or an asymmetry that could not be explained by ordinary fluctuations. These ideas are speculative, but they show how cosmology tries to turn even bold possibilities into testable questions. So far, no widely accepted sign of another bubble universe has been found. That does not prove such bubbles do not exist. It means that if they do, they have not left a clear mark we can identify in our observable sky. The absence of evidence is not always evidence of absence, but it does limit what we can responsibly claim. The universe is allowed to be mysterious. We are not allowed to pretend it has whispered something it has not. Another possible clue comes from the geometry of space. If the universe were finite and wrapped around on itself in some way, we might see repeated patterns in the sky. The same region of space could appear in different directions, its light having travelled along different paths. Astronomers have looked for repeated patterns in the cosmic microwave background and in the arrangement of distant objects. So far, there is no convincing evidence that our observable universe wraps around in a detectable way. This suggests that if space has such a shape, it is larger than the region we can observe, or the topology is not one that produces obvious repeats. Again, this does not give us a final answer about the whole universe. It narrows the possibilities. It tells us what the universe is not doing within our view. The expansion of the universe also gives us clues and limits. By measuring how galaxies move away from us, how ancient light has been stretched, and how cosmic structure has grown, scientists reconstruct the expansion history of space. This history points to a universe that began hot and dense, expanded and cooled, formed atoms, stars, galaxies and clusters, and is now expanding at an accelerated rate. That acceleration matters for knowing the beyond because it creates a future horizon. There are regions whose light emitted now will never reach us. We may see old light from some galaxies, but never their present or future light. Over vast times, more and more distant galaxies will fade beyond practical detection. This means there are limits not only on what we know now, but on what any future observer in our region may ever know. The universe is not simply waiting for better instruments. In some directions and at some distances, the information is physically unavailable. That is a hard idea, but it is not a defeat. It is a map of the boundary. Science often advances by learning where the walls are. A wall can be frustrating, but it can also tell you the shape of the room. The cosmic horizon tells us that the universe is not fully accessible from any one location. It tells us that our knowledge is local in a deep sense. We do not stand outside reality with a complete view. We are inside it, receiving signals that have crossed expanding space. This makes cosmology different from studying a stone on a table. We cannot pick up the whole universe, turn it around, and inspect the underside, which is perhaps fortunate since the table would have to be rather sturdy. We study what reaches us, then use physical laws to infer what cannot. The reliability of those physical laws is another key question. When we use observations inside our horizon to infer what lies beyond, we assume that the laws of physics continue to apply. This assumption is not arbitrary. It has worked astonishingly well across the observable universe. Light from distant galaxies carries the signatures of atoms behaving in familiar ways. Gravity shapes galaxies and clusters in ways consistent with the same principles we test nearby. The cosmic microwave background matches predictions built from known physics, extended into earlier conditions. The success of these models gives us confidence that the laws are not changing wildly within our observable region. But beyond the horizon, we cannot verify them directly. We can reasonably extend them, especially just beyond what we see. But at some point the extension becomes more uncertain. The farther the inference reaches, the more carefully it must be held. This is especially true for multiverse ideas. If another bubble universe is permanently disconnected from ours, can we ever know it exists? The honest answer is maybe only indirectly, and perhaps not at all. If the theory that predicts such bubbles also makes successful predictions inside our observable universe, then the bubbles may become a serious consequence of a good theory. But if they leave no observable trace and the theory cannot be tested in other ways, then the idea remains speculative. It may be mathematically interesting, it may be philosophically rich, it may even be true. But science needs a connection to evidence. Without that connection, we drift from cosmology into storytelling. And while storytelling is a noble human activity, it should not be mistaken for measurement, even when the story has excellent lighting and a very confident narrator. A useful distinction is between what is directly observed, what is inferred, and what is possible. Directly observed means signals have reached us. Inferred means the best explanation of observed signals points to something unseen. Possible means a theory or imagination allows it, but evidence has not established it. Beyond the observable universe, most of our statements live in the inferred or possible categories. More universe beyond the horizon is strongly inferred from the smoothness and scale of what we see. An infinite universe is possible and consistent with current observations, but not proven. A finite, unbounded universe is possible, but not demonstrated by repeated patterns. Other bubble universes are possible in some inflationary theories, but not observed. Different physical laws beyond our domain are possible in some theoretical landscapes, but remain uncertain. Keeping these categories separate is not dry bookkeeping. It is how we avoid fooling ourselves. The desire to know what is beyond is very human. Horizons bother us. They invite us. A child looking past the end of a road wants to know where it goes. Sailors crossed oceans because the horizon did not satisfy them. Astronomers built telescopes because the naked eye was not enough. In many cases, horizons have yielded. The moon became a place. Planets became worlds. Nebulae became galaxies. The Milky Way became one galaxy among many. Each time we extended our reach, the universe became larger and less centered on us. So it is natural to wonder whether the cosmic horizon is just another temporary boundary. Perhaps future physics will reveal new messengers. Perhaps gravitational waves from extremely early times will tell us more. Perhaps patterns in the cosmic background will reveal deeper structure. Perhaps new theories will connect the visible and hidden in ways we have not yet imagined. Science is not finished. It would be rather awkward if it were, because many people have meetings scheduled. But the cosmic horizon may not yield in the same way earlier horizons did. The horizon at sea can be crossed by sailing. The horizon of the naked eye can be crossed by telescopes. The horizon of visible light can be crossed by radio, infrared, X-ray, and gravitational wave astronomy. But the horizon of causal contact is different. If no signal from a region can ever reach us, then no instrument, however clever, can collect information from it directly. That does not mean future knowledge cannot improve. It means there may be a final limit to direct observation. The universe can contain places that are real but unreachable in principle. Accepting that is part of the maturity of cosmology. It is the scientific version of admitting that not every cupboard in the house can be opened, even if one strongly suspects there are biscuits inside. There is also a philosophical question underneath all this. What does it mean to know something that cannot be observed directly? In everyday life, we accept many kinds of indirect knowledge. If you see wet footprints across the floor and a dog looking guilty beside an open garden door, you infer something happened even if you did not see the puddle incident itself. In science, the standards are much stricter, but the logic is similar. A theory gains strength when it explains many observations, makes accurate predictions, and fits together with other well-tested ideas. If that theory implies something beyond direct observation, we may take the implication seriously, but we also mark it as dependent on the theory. If the theory changes, the implication may change. This is why scientists speak carefully. They might say observations are consistent with a much larger universe, or inflation suggests regions beyond our horizon, or some models predict other bubbles. Those careful phrases are not weakness, they are honesty. In the future, there may be new kinds of evidence. Measurements of the cosmic microwave background may become even more precise. Observations of the large-scale structure of galaxies may improve. Gravitational wave astronomy may eventually probe processes from much earlier cosmic times than light can show us. Studies of dark energy may reveal whether the accelerated expansion is constant or changing. Better understanding of particle physics may clarify what drove inflation, if inflation truly occurred. Each improvement could sharpen our picture of what lies beyond. We may learn that certain models are wrong. We may find stronger support for others. We may discover that the early universe behaved in a way no current model fully captures. The hidden regions may remain hidden, but the boundary around our ignorance can move. That is a comforting way to think about knowledge. We may not be able to illuminate everything, but we can often illuminate the shape of the darkness. We can say not just we do not know, but here is why we do not know. Here is what the evidence suggests. Here is what remains possible, and here is what would change our minds. That is much better than a blank shrug. The observable universe is not a prison for thought. It is the evidence base from which thought responsibly begins. The horizon limits direct sight, but it does not silence reason. So can we ever know what is beyond? We can know some things with reasonable confidence. We can know that the observable edge is not likely to be a physical edge where space stops. We can know that our visible universe appears to be part of a larger, smooth, cosmic structure. We can know that inflation, if correct, would make the full universe far larger than what we see. We can know that current observations allow the universe as a whole to be much larger than our bubble, perhaps infinite, though they do not prove infinity. We can know that some speculative possibilities, like bubble universes, are serious ideas in certain theories but not confirmed facts. We can know the difference between evidence and imagination, which is a very useful thing when standing near the edge of everything. What we may never know are the details of specific regions beyond permanent horizons. We may never know the exact arrangement of galaxies in places whose light will never arrive. We may never know whether a particular unseen star formed, or whether a planet beyond our cosmic reach has oceans under a pale sky. We may never directly observe another bubble universe, if such things exist. The universe may have a full reality larger than any possible observation from within our region. That is not a failure of human intelligence. It is a feature of living inside an expanding space-time. There is a quiet beauty in that. The unknown beyond the observable universe is not simply a gap waiting to be filled. It is a reminder that reality does not owe us complete access. We learn what we can through the light that reaches us, the patterns it carries, the physics it reveals, and the careful reasoning that follows. We stand inside a bubble of ancient messages, reading them as well as we can. Beyond the bubble, the universe may continue in familiar ways, or it may widen into possibilities we cannot test. Either way, the horizon teaches us both curiosity and restraint. It asks us to imagine, but not to pretend, to infer, but not to overstate, to keep looking even when looking has limits, and perhaps that is a fitting place to rest before we let the journey soften toward its close. We have not reached a wall at the end of space. We have reached the edge of what can be known from here for now. Around us is the observable universe, bright with galaxies and old light, filled with evidence of a long cosmic history. Beyond it may be more of the same vast structure, or something stranger on scales we cannot touch. The answer remains partly hidden, but not empty. It waits beyond the glow of our lantern, while here inside the light, we continue to listen, measure, wonder, and slowly piece together what the visible universe can tell us about everything just out of sight. And so, dear listener, we have drifted to the edge of what can be seen from here, though not to the edge of the universe itself. That is an important distinction, and a strangely comforting one. We have not arrived at a wall. We have not reached a final border where space folds up its map, puts on a hat and says, That is quite enough for one evening. What we have reached is the limit of our view, the place where the oldest light has given us all it can, where distance and time and expansion gently close the curtain. Beyond that curtain, the universe may continue in much the same way, with more galaxies, more dark spaces between them, more stars quietly forming from cold gas, more planets circling suns whose light will never touch our sky. Or perhaps, on scales too vast for us to measure, the cosmos changes in ways we cannot yet know. The honest answer is that some things remain hidden, but hidden does not mean empty. It simply means the universe is larger than the circle of light around our little lantern. It is worth pausing with that image, because it brings the whole question back down to something almost familiar. Imagine again standing in a wide field at night. You hold a lantern, and it shows you the grass around your feet, the shape of a path, the low branches of a nearby tree. Beyond the glow there is darkness, but the darkness is not nothing. It is the rest of the field. Maybe there is a fence out there, maybe a hill, maybe a very confused sheep wondering why someone is discussing cosmology in its meadow. You cannot see everything, but what you can see tells you that the land continues. The observable universe is like that lantern glow. It is not small, not in any human sense. It contains hundreds of billions of galaxies, a history stretching back to the first freely travelling light, the great cosmic web, the traces of inflation, the slow work of gravity, the birth and death of stars, and the ingredients from which planets and people are made. Yet even all of that may be only the illuminated patch. There is something deeply humbling about being alive inside such a patch. We are tiny, yes, but not separate. The atoms in our bodies belong to this same cosmic story. The hydrogen in you is old, older than stars. The heavier elements were made in stellar furnaces and scattered through space by ancient explosions. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in every cell, all of it was shaped by the long history of the observable universe. So when we ask what lies beyond it, we are not asking from outside the story. We are the story asking about its unseen pages. We are pieces of the universe that have learned to wonder how far the rest of the book might go, which is rather impressive for a species that also regularly loses its keys while holding them. The journey began with a simple question: what is beyond the observable universe? At first it sounded like a question about distance, as if we only needed to build a stronger telescope and look a bit farther. But it became a question about light, time, expansion, and the limits of information. The observable universe is defined by what has been able to reach us. Light from distant galaxies carries their past into our present. The deeper we look, the younger the universe appears. The oldest light we can see comes from the time when the universe became transparent, when the cosmic fog cleared enough for radiation to travel freely. Before that, ordinary light cannot give us a direct picture. Beyond our present horizon, other regions may exist whose signals have not reached us. Some may never reach us at all. The edge is not made of matter, it is made of history. That idea changes the meaning of looking up. The night sky is not a ceiling. It is not a flat darkness with stars pinned to it like decorations on a very ambitious blanket. It is depth. It is time. It is a collection of delayed messages arriving from different ages of the universe. Nearby stars show us a recent past. Distant galaxies show us ancient eras. The faint background glow shows us the universe in its early transparent state. And beyond the reach of that glow, beyond the reach of any signal arriving here, the full universe may continue silently. Not silent because nothing happens there, but silent to us. Because no message can cross the widening distance. Somewhere beyond our horizon, a galaxy may be shining beautifully, but its light is not part of our sky. Somewhere, perhaps, stars are dying, planets are forming, and chemistry is unfolding under constellations we will never name. This can feel like a loss at first. Humans like to know. We like to open doors, cross oceans, climb mountains, map coastlines, peer into microscopes, launch probes, and ask questions that make everyone at dinner either fascinated or suddenly very interested in dessert. A horizon that cannot be crossed by observation feels almost rude. But there is another way to see it. The existence of a horizon does not make the universe less wondrous. It makes the universe larger than our possession of it. We do not own reality by observing it. We meet part of it. We learn from the light that reaches us. We build careful models from the evidence available, and then, with a little humility, we admit that beyond the evidence there may be more than we can ever directly know. That humility is not the same as giving up. Science has always lived between curiosity and restraint. It reaches outward, but it also labels its steps. This is observed. This is inferred. This is possible. This remains unknown. That careful sorting may not sound as dramatic as declaring that infinite bubble universes are definitely having a party beyond the cosmic horizon, but it is much more useful and probably better for sleep. We know that the observable universe is not likely to be the whole of existence. We know that its large-scale smoothness suggests a much larger continuation. We know that inflation, if it happened as many models suggest, would have stretched space far beyond the part we can see. We know that some theories allow other cosmic domains, perhaps with their own histories and conditions. But we also know that these ideas must be treated with care. The universe rewards imagination, but only when imagination agrees to sit beside evidence and not wander off into the garden unsupervised. Perhaps the most grounded answer is also the most quietly astonishing. Beyond what we can see, there is probably more universe, not an edge, not a drop into nothing, more space, more matter, more cosmic web, more great voids, more galaxies whose light is too far away, too delayed, or forever unreachable. That may sound simple, but simple is not small. More universe is already an answer big enough to overwhelm the mind. If our observable bubble is only one patch, then the whole may be vastly larger than anything we can ever map. It may be finite but beyond detection. It may be infinite. It may curve in ways too subtle for us to measure. It may contain regions that remain forever outside our contact. And if some more speculative ideas are right, it may even be one domain among many. The horizon does not give us a single final picture. It gives us a range of possibilities, each stretching the mind a little farther than the last. There is a gentle irony in the fact that the farther outward we look, the more we learn about beginnings. The edge of our view is old. The deepest light is young. The distant universe shows us the past, not the present. So when we ask about the farthest things, we are also asking about the earliest things. What is beyond the observable universe is tied to what happened before the oldest light we can see, to inflation, to the conditions that set the stage for galaxies, to the first tiny variations that gravity later turned into structure. The question outward becomes a question backward. Space and time fold together in our understanding, not as a poetic flourish, but as the practical reality of light taking time to travel. To look far is to look young. To ask what lies beyond is to ask what our visible history cannot reach. And still, here we are inside the visible part, with enough light to tell a remarkable story. We have learned that the universe is expanding. We have learned that it was once hotter and denser. We have measured the ancient glow left from its early transparent era. We have mapped galaxies across enormous distances. We have found that ordinary matter, the stuff we touch and taste and occasionally spill on a clean shirt, is only a small part of the cosmic contents. We have inferred dark matter from gravity and dark energy from expansion. We have traced the growth of structure from tiny early variations to the vast cosmic web. For creatures on one small planet, with eyes adapted originally for sunlight and survival, that is not a bad effort at all. It is also a reminder that knowledge does not require total knowledge. We do not need to see the whole universe to understand something profound about it. A single shell can tell you about the sea. A fossil can tell you about an ancient life. A faint microwave glow across the sky can tell you about the early cosmos. The observable universe is not everything, but it is rich enough to speak. Its light has crossed billions of years to reach us. Its patterns have survived expansion, cooling, gravity, and time. It has given us clues so delicate that they might have been missed, and yet human beings built instruments precise enough to catch them. There is something very moving in that. The universe whispered, and eventually, after a great deal of trial, error, mathematics, engineering, and probably coffee, we learned how to listen. Maybe that is the feeling to carry at the end of this journey. Not that we have solved the entire mystery, but that the mystery has become clearer. The observable universe is our cosmic home, not because it is all that exists, but because it is the region connected to us by signals. Its edge is a horizon, not a wall. Beyond it, the simplest expectation is more of the same vast cosmos. On greater scales, there may be possibilities we cannot yet confirm. Some may remain forever unreachable, but the boundary itself has meaning. It teaches us about light. It teaches us about time. It teaches us about expansion. It teaches us that every observer lives inside a view, and that every view has limits. So, as the mind begins to quiet, you might picture Earth from far away. Not as the centre of anything, not as a throne, not as the special seat reserved in the cosmic theatre, but as a small world circling an ordinary star in one galaxy among many. Around it, in every direction, light arrives from the past. The glow of nearby stars, the faint smudges of distant galaxies, the ancient background radiation from a younger universe. And beyond all that, unseen regions continue, or may continue, outside the reach of our oldest messages. Earth is not central, but it is included. And so are we. We are local, temporary, fragile, and yet capable of thinking about horizons larger than any journey we can take. There is peace in that scale, if we let it be peaceful. The universe is not asking us to hold all of it in our heads at once. That would be unreasonable and frankly a little impolite. It offers instead a view, a set of clues, and a question large enough to soften the edges of everyday worry. The emails, the errands, the misplaced cup, the small frustrations of the day, all of them are real in their human way. But they exist beneath a sky whose light has travelled for billions of years, inside a universe whose visible part may be only the beginning of what is there. Sometimes scale does not make our lives meaningless. Sometimes it makes them gentler. It reminds us that we are part of something vast, and that even not knowing can be restful when it is held honestly. And now, as we return from the edge of everything we can observe, I want to ask again what I asked at the beginning. Where are you listening from tonight? What does the sky look like in your corner of the world? Maybe you're beneath city lights, where only a few bright stars manage to appear. Maybe you're somewhere dark where the Milky Way stretches overhead like a pale river. Maybe you cannot see the sky at all from where you are, but it is still there above the roof, above the clouds, above the turning earth. And beyond it, far beyond anything your eyes could gather, the observable universe spreads outward in every direction, carrying its ancient messages toward us. Beyond that, the rest remains hidden, not empty, not forgotten, simply beyond the glow. If this quiet journey has given your thoughts somewhere calm to wander, or helped the day loosen its grip a little, I would be ever so grateful if you liked the video, subscribed, and shared this sleepy corner of science with someone else who might enjoy drifting through the universe at a gentle pace. It helps these slow voyages reach other curious listeners, perhaps someone lying awake right now, wondering whether the universe has an edge, or whether the darkness beyond the stars goes on and on and on. And if you have made it this far without falling asleep, that is perfectly all right too. All right. You have spent the time resting at the boundary of human knowledge, which is a rather fine place to be. The observable universe is not all there may be. It is all that has reached us. It is the lantern glow around our world, filled with galaxies, ancient light, and the long memory of cosmic beginnings. Beyond it, the universe may continue beyond all maps, beyond all signals, beyond every telescope we will ever build. We may never know its full size, we may never see its farthest regions, but here, inside the light we have received, we can still wonder, we can still measure, we can still listen, and for tonight that is enough. Let the horizon remain where it is, let the unseen universe be unseen, let the stars near and far keep their patient watch. Sleep well, fellow traveller, here inside our small bright bubble, at the quiet edge of everything we know.